Tonight, something a bit different, a 4-hour compilation. First up, we explore some of the heaviest objects in the universe, and how they are so dense they stop time. Then we move on to our missing planet Vulcan, which has nothing to do with Star Trek, and everything to do with how astronomers in the 19th and early 20th centuries were convinced there was a planet between Mercury and the Sun. We then move on to the idea that it is highly probable that there is life on Mars, as there is plenty of evidence for it. We go through the 1970s discoveries, the methane discovery, the stone that looks like it has fossils, and a lot more. We end with the manned mission to Titan. It's not science fiction. It is literally the beginnings of a plan to send humans to Titan after the Moon and Mars, but we mainly cover Titan and what we'll do on Titan when we get there. Sleepy Star Science is all about delivering to you a nice, relaxing video to fall asleep to with amazing scientific facts narrated in a relaxing way, accompanied by some fantastic video and images representing various places in the universe. I hope you enjoy this compilation, and I look forward to your presence again for our next one. Now, let's begin. Picture a single spoonful of matter suddenly appearing above your table. It looks like nothing much, a small lump about the size of a sugar cube, and then it falls. Straight through the table, through the floor, through the rock beneath the house, down into the planet, because that little lump weighs as much as an entire mountain range. This is real material, scooped from a real object circling somewhere in the sky above you tonight, and it carries a secret that runs even deeper than its impossible weight. Where matter is crushed together this tightly, time itself begins to slow. A clock sitting on the surface of that lump would tick more lazily than the watch on your wrist, falling further and further behind with every passing second. Tonight we're going hunting for the heaviest objects in the entire universe, and we're going to follow what their crushing weight quietly does to time. If the idea of drifting out through the cosmos in search of its most extreme places sounds like a pleasant way to spend the next while, then a quiet like or a subscribe genuinely helps this small channel keep making these journeys. Settle in, get comfortable, let your shoulders drop and your breathing slow. We have a long and gentle climb ahead of us, and we're going to start somewhere reassuringly familiar before things become strange. Let us begin with the word heavy, because it is going to mislead you almost immediately if we are not careful. In everyday life, heavy means hard to lift. A bag of shopping, a sleeping cat, a large sack of rice. But out in space there is a deeper quality at work, and astronomers call it mass. Mass is the amount of stuff a thing is actually made of, the sheer quantity of matter gathered into one place. And mass does something remarkable. It reaches out into the space around it and pulls. We call that pull gravity, and you have felt it every single day of your life without ever once being able to see it. For a long time, people thought of gravity as a kind of invisible rope, a force tugging objects toward each other across empty space. Then, a little over 100 years ago, a patent clerk with wild hair and a quiet stubbornness named Albert Einstein worked out that the truth was far stranger and far more beautiful. Gravity, he realized, is not a rope at all. It is the bending of space and time. A heavy object sinks into the smooth fabric of reality, the way a bowling ball sinks into a soft mattress, and everything nearby rolls inward along the slope it makes. The heavier and the more tightly packed the object is, the deeper the dent and the steeper the slope. And here is the part that will quietly haunt the rest of our night together. that dent does not only bend space, it bends time. Down inside a deep gravitational well, close to a great mass, time genuinely runs slower than it does far away in open space. This is not a trick of perception, or a feeling, or a metaphor. It is measurable, and it has been measured over and over again. The closer you sit to a concentration of mass, the more slowly your own clock ticks compared to a clock left behind out in the emptiness. The whole journey tonight is really one long climb up a ladder, and on each rung we will find a heavier, denser, more crushing object than the one before. And on each rung, as the weight grows, time will lean a little further out of step, until at the very top we reach a place where it nearly stops altogether. So let us put our first foot on the bottom rung, and the bottom rung is our own sun. By the standards of your kitchen, the sun is unthinkably heavy. You could pour roughly 1/3 Earths into it and still have room to spare. It holds more than 99% of all the mass in the entire solar system, which means that everything else, all the planets, every moon, every asteroid and comet and wandering speck of dust, is really just crumbs left over around the edge of the table. The sun is so massive that its gravity keeps the Earth swinging around it from a distance of 93 million miles, and keeps distant Neptune leashed to it from nearly 3 billion miles away. And yet, for all that, the sun barely touches time at all. If you could stand on its blazing surface, holding a stopwatch, and compare it later with one left floating far out in deep space, you would find that your solar stopwatch had lost only a couple of seconds across an entire year. A tiny stumble, a few heartbeats lost in 12 months. The sun is heavy, but it is also enormous and puffy and spread out. A vast loose ball of glowing gas more than 800,000 miles across. Its mass is smeared over such a huge volume that the dent it makes in time, while real, is shallow. You do not even have to go to the sun to find this effect, by the way. It is happening to you, right now, in your own home, in a way so small you will never feel it. Because the Earth has mass too, and so the closer you are to the centre of the planet, the slower your time runs. Your feet, resting on the floor, are very slightly deeper in the Earth's gravity than your head is, which means, strictly speaking, that your head is aging a hair faster than your feet. Over a lifetime, it adds up to a few billionths of a second, which is a wonderfully useless fact to carry around, and I am delighted to be the one to give it to you. These satellites that run the navigation in your phone take this far more seriously than your head and feet ever will. They circle high above us where the Earth's gravity is weaker and time runs a touch faster, and engineers have to correct their clocks for it constantly. If they did not, the maps in your pocket would drift wrong by several miles every single day. So that is the gentle truth we are carrying up the ladder. Mass bends time, and we have already felt the very first faintest whisper of it. Now let us leave the warm and the familiar behind, and climb to the second rung, where a star like the sun goes to die. Every star is a slow and patient war between two enormous forces. Gravity is forever trying to crush the star inward, to collapse all that gas down into the centre, and the nuclear fire burning in the core is forever pushing outward, holding the star up, keeping it round and bright and stable. For billions of years, these two forces stay almost perfectly balanced. But the fire needs fuel, and the fuel does not last forever. One day, far in the future, our own sun will burn through the last of the hydrogen at its heart, and the long war will start to turn. When that happens, the sun will not explode. It is not heavy enough for the truly violent ending. Instead, it will swell up into a vast bloated red giant, large enough to swallow the closest planets, and then it will gently shrug off its outer layers into space in glowing rings. What it leaves behind, sitting alone in the dark, is the bare, exposed core, and that core is the second rung of our ladder. It is called a white dwarf. A white dwarf is the burnt-out ember of a star, and it is one of the strangest objects you will ever try to picture. Take the mass of something like the Sun, hundreds of thousands of times the Earth, and crush it down until it is no bigger than the Earth itself. That is a white dwarf, roughly a sun's worth of material, squeezed into a ball the size of our little planet. The matter inside is so compressed that a single spoonful of it would weigh several tons, as much as an elephant balanced on a teaspoon. The gravity at its surface is around 100,000 times stronger than the gravity holding you in your chair right now. What holds a white dwarf up now that its fire has gone out is one of the deep and quiet rules of the quantum world. The tiny particles called electrons that make up part of all ordinary matter simply refuse to be packed too closely together. They push back, not with heat, not with fire, but with a stubborn quantum pressure that comes from the rules of reality themselves. This stubbornness is strong, but it is not infinite. There is a line it cannot hold beyond. An Indian physicist named Subramanian Chandrasekhar worked out exactly where that line falls back in the 1930s when he was barely 20 years old, doing the calculations on a long sea voyage. He found that if a white dwarf carries more than about 1 4/10 times the mass of the Sun, the electrons lose their fight, and the object can no longer hold itself up. That limit still carries his name today. So a white dwarf sits there, Earth-sized, sun-heavy, cooling slowly over billions and billions of years, fading from white to yellow to a dull, dim red, and finally, in a future further away than the present age of the universe, to cold and dark. The densest white dwarfs we have found are even smaller and fiercer than the average, packing all that mass into a sphere closer to the size of our moon. And now, because we have climbed a rung, time has shifted again. Stand on a white dwarf with a stopwatch, and you would lose far more than a couple of seconds a year. You would now lose minutes. The dent in time has deepened from a shallow scoop into something you could genuinely notice if you could survive the visit. It is still a whisper rather than a shout, but it is a louder whisper than the Sun could ever manage, because the same amount of mass is now crushed into a space 10,000 times smaller, and the slope down into its gravity is correspondingly steeper. Remember that idea, because it is the secret engine of this whole night. It is never simply how much mass an object has, it is how tightly that mass is squeezed. Hold on to that, because the next rung is going to take it and run. For the third rung, we need a star that was born much heavier than the Sun, a star perhaps 8 or 10 or 20 times the Sun's mass. These giants live fast and die young. Where our Sun will burn quietly for 10 billion years, a massive star like this races through its fuel in just a few million, blazing with the light of 100,000 suns, and then it comes to an ending so violent it briefly outshines an entire galaxy. When a massive star finally runs out of fuel, the long war ends all at once. There is no slow swelling, no gentle puff of rings. The core, no longer held up by fire, collapses in on itself in less than a second. The outer layers come crashing down onto that collapsing core, rebound and tear outward in a colossal explosion called a supernova. For a few weeks, that single dying star can shine brighter than all the billions of other stars in its galaxy put together. And in the ruins at the center of that explosion, something new is born. Something that should not, by any everyday intuition, be able to exist at all. It is called a neutron star, and it is the fourth thing on our list and the third real rung of our climb. When the core of that massive star collapses, gravity becomes so overwhelming that it does something almost unbelievable. It crushes the atoms themselves. Normally, an atom is mostly empty space, a tiny dense center with even tinier particles whirling far out around it, like a single fly in the middle of a cathedral. But in the collapsing core, gravity slams everything together so hard that the empty space is simply squeezed out. The particles are jammed into contact. The protons and electrons are crushed together into neutrons, and what remains is a ball of pure crushed matter packed as tightly as the center of an atomic nucleus. Now hold the scale of this in your mind gently, because it is genuinely difficult for a human brain to hold. A neutron star contains more mass than the entire Sun, and it is squeezed into a sphere only about 12 to 15 miles across. You could lay a neutron star down across a single city, and it would not reach the suburbs. A mass greater than our star, packed into something you could circle on a bicycle in an afternoon, if the gravity and the heat and the radiation did not vaporize you in the first fraction of an instant. The density is the thing that breaks the imagination. Remember the spoonful of matter that fell through the table at the start of the night. This is where it came from. One sugar cube of neutron star material weighs about 1 billion tons. If you could somehow bring a single thimble of the stuff back to Earth, it would punch straight down through the ground and fall toward the center of the planet, because nothing in our ordinary world is remotely strong enough to hold it up. The gravity at the surface of a neutron star is around 200 billion times stronger than Earth's. A marshmallow dropped onto its surface would hit with the energy of an atomic bomb, and these objects spin, often terrifyingly fast. As the great core collapsed, it pulled its rotation inward and sped up, the same way a spinning figure skater whips faster when they pull in their arms. Some neutron stars turn hundreds of times every second, a city-sized ball of crushed matter whirling so fast that its surface moves at a sizable fraction of the speed of light. As they spin, many of them sweep beams of radiation across space like a lighthouse, and each time the beam crosses the Earth, our instruments catch a pulse, steady and precise, ticking out across the galaxy. We call those ones pulsars, and the first time one was discovered, the signal was so regular that astronomers half-jokingly labelled it LGM, for little green men, before they understood they were hearing the heartbeat of a dead star. And what about time, here on the third rung? This is where the whisper finally becomes something you could never ignore. On the surface of a neutron star, time does not stumble by a few seconds, or fall behind by a few minutes. It runs slow by something like 20 to 30%. Think carefully about what that means. If you could stand on a neutron star and survive for what felt to you like 10 years, you would return to find that far out in the safety of open space. 13 years had gone by. Friends would have aged faster than you. The calendar would have run ahead. The crushing weight beneath your feet would have genuinely stolen time out from under you and handed it to the rest of the universe. We have climbed only 3 rungs, and already we have reached a place where a clock loses nearly 1/3 of its life to gravity. We do not fully understand what lies at the very center of a neutron star, and I want to be honest with you about that, because the honest mysteries are some of the most beautiful parts of this. The pressure deep inside is so far beyond anything we can make in a laboratory that the matter there may take forms we've never seen. Some scientists suspect the neutrons themselves may break down into an even stranger soup of the tinier particles called quarks. Others propose still odder possibilities with names like strange matter. These ideas are educated guesses, clearly marked as guesses, sitting at the frontier of what physics can currently reach. What is certain is the weight and the smallness and the way time bows down before them. Now, a neutron star is already one of the most extreme things in creation, but the universe, it turns out, was not finished. Because some neutron stars carry one more property, dialed up to a level so absurd that for years physicists were not sure such an object could be real. And that brings us to the fourth rung, and to a kind of object whose name sounds like it came straight out of a comic book, the magnetar. A magnetar is a neutron star with all the crushing weight and slowed time we've just described, but wrapped in a magnetic field so powerful it almost defies belief. You know magnetism, the little magnet on your fridge, the compass needle swinging gently to point north. The Earth itself is a giant weak magnet, which is what that compass is feeling. A magnetar's magnetic field is around 1,000 trillion times stronger than the Earth's. Not 1,000 times, not 1,000,000, 1,000 trillion. It is, as far as we know, the strongest magnetic force anywhere in the entire universe. A field that strong does not just move compass needles, it warps reality. Get within a few thousand miles of a magnetar, and its magnetism would reach into your body and pull you apart at the level of your atoms, because the very shape of the particles in your cells cannot survive a field like that. The empty space around a magnetar becomes unstable, almost boiling, with particles flickering in and out of existence under the sheer strain. These are objects so extreme that they bend not only space and time but the rules of matter itself. And now and then, a magnetar does something that reaches all the way across the galaxy and touches us. On the 27th of December 2004, an alarm of sorts went off all over the Earth. Satellites flinched. Instruments designed to study the heavens momentarily saturated and went blind. For 0.2 seconds, a wave of radiation washed over our planet, and it had come from a magnetar called SGR 1806-20, sitting roughly 50,000 light-years away on the far side of the Milky Way from us. Let me try to make the scale of that flash real, because the numbers alone slide off the mind. In those 0.2 seconds, that single object released more energy than our sun pours out in 250,000 years. A flicker shorter than a blink carrying 250,000 years of sunshine. It had travelled 50,000 years across the galaxy to reach us, and even after all that distance, even from the far side of the Milky Way, it was strong enough to measurably disturb the upper atmosphere of the Earth and ionize the air high above our heads. Astronomers who had spent their entire careers studying violent events in space said they had simply never seen anything like it. Had that magnetar been sitting a few light years away instead of 50,000, the burst would have stripped away our planet's protective ozone layer in an instant. The thing released all that fury during a kind of starquake, a sudden cracking and resettling of its impossibly rigid crust, letting its monstrous magnetic field snap and reconnect like a coiled spring finally let go. We know of only a few dozen magnetars in our galaxy, and they do not announce themselves. They sit silent in the dark for years, decades, centuries, bleeding their magnetic energy quietly into space. And then, without warning, one of them fires. They are perhaps the most genuinely frightening objects we have met so far tonight, and yet they sit on the same rung as the ordinary neutron star when it comes to time, because their weight and their size are much the same. Their horror is magnetic, not gravitational. To deepen the dent in time any further, we cannot just add magnetism. We have to add mass. We have to find a neutron star pushed right to the very edge of what it can possibly hold, which is exactly the fifth rung. Because not all neutron stars are equal. Most carry somewhere between 1.5 and 2 times the mass of the Sun. But astronomers have been searching for the heaviest ones they can find, the record holders, the neutron stars sitting closest to the breaking point, and the current champion is an object with the unlovely catalogue name of PSRJ 0952-0607. It is what astronomers affectionately call a black widow. It earned that grim nickname honestly. This neutron star is locked in a close embrace with a companion star, and over millions of years it has been doing something rather monstrous to its partner. Its ferocious gravity and radiation have been stripping the companion apart, pulling its material away and devouring it, the way a black widow spider consumes its mate. By feeding on its companion in this way, the neutron star has grown unusually fat and unusually fast. It now spins 707 times every single second, which is so fast it is almost impossible to picture. A city-sized ball of the densest matter in the cosmos, whirling more than 700 times around in the time it takes you to say the word once, and by eating it has grown heavy. As of the most recent and careful measurements, finished only this year, this black widow weighs about 2.33 times the mass of our Sun. That may not sound like a dramatic figure after all the billions and trillions we've been throwing around, but in the world of neutron stars it is enormous. It sits right at the theoretical edge, the absolute limit of how much mass-crushed matter can possibly bear before it loses the fight entirely. One more decent meal, one more substantial mouthful of its companion, and the electrons and neutrons and whatever else holds it up would finally surrender, and it would collapse into something else. Something from which nothing returns. It is matter holding itself open at the very last possible instant before the floor gives way. And so, on this rung, time bends about as far as crushed matter can make it bend while still remaining matter at all. On the surface of this overfed neutron star, balanced at the brink, clocks run slow by something approaching 1/3, deeper than any ordinary neutron star, as deep as solid stuff can manage. To go any further down into the well of time, the object can no longer stay an object. It has to fall over the edge. But before we follow it over that edge, I want to pause and clear up a misunderstanding that has probably been quietly building in your mind, because we are about to take a sharp and surprising turn. All night we've been climbing toward heavier and heavier things, and you might reasonably assume that the heaviest single object we could find, the most massive star in the sky, would be the deepest dent of all in time. So let us go and visit it. It is called R13601, and it lives about 160,000 light-years away, inside a glittering nursery of newborn stars called the Tarantula Nebula, in a small galaxy that drifts alongside our own Milky Way. R13601 is a true monster of a star. For years, astronomers argued about exactly how heavy it is, with early estimates running wildly high, and the most careful recent measurements settling it at around 196 times the mass of our Sun. Let that sit for a moment. Almost 200 suns gathered into one single blazing star. It is one of the most massive stars known to exist anywhere. It burns at a temperature 7 times hotter than the surface of our Sun, and it shines with something close to the light of 10 million suns. It is so violently bright that it is tearing itself apart, flinging its own outer layers off into space in a furious wind, shedding the weight of an entire Earth every few days. So here is the most massive star we know, almost 200 suns of mass. Surely this is where time slows the most, and the answer, the lovely and instructive answer, is no, not even close. Stand near R13601 with your stopwatch and time would barely flinch. It would lose perhaps a little more than the Sun does, and nothing remotely like a neutron star. This enormous star with a mass of 200 suns bends time less than a dead cinder 1/10,000th its weight, and that is the whole secret of the night laid bare in a single comparison. R13601 has staggering mass, but it is also vast and bloated and spread thin. All those 200 suns of material are smeared across a star so wide that if you placed it where our Sun sits, its surface would reach out a good fraction of the way toward the inner planets. The mass is there, but it is diffuse, scattered across an enormous volume, so the slope down into its gravity is gentle. The neutron star, by contrast, took less mass and crushed it into a ball the size of a city, and that fierce concentration is what dug the deep well in time. It was never about how much. It was always about how tightly. The most massive star in the sky is a gentle giant, in the literal sense that its grip on time is gentle. To truly stop time, you do not need the most mass. You need mass that has finally lost its battle and collapsed all the way down. You need the thing that waits for us on the 6th rung. You need a black hole. When a star far heavier than the Sun dies, or when an overfed neutron star takes that one last fatal mouthful, gravity wins the war completely and forever. There is no quantum stubbornness left that can hold the matter up. The core collapses, and it does not stop at the size of the Earth like a white dwarf, and it does not stop at the size of a city like a neutron star. It keeps falling inward, smaller and smaller and denser, and as far as our current physics can tell, it does not stop at all. The matter collapses down toward a single point of infinite density, a place where our equations themselves throw up their hands and stop giving sensible answers. We call that point the singularity, and the honest truth is that we do not understand it. It is one of the great unsolved questions in all of science. But the singularity is not the part you would actually meet. Around it, at a certain distance, there is a boundary. It is not a surface, not a wall, not anything you could touch. It is a line drawn in space, a point of no return, and it is called the event horizon. The event horizon is the place where the slope into the black hole's gravity becomes so steep that the speed you would need to climb back out exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses that line can ever come back. Not a spaceship, not a beam of light, not a cry for help. The event horizon is the edge of a one-way door, and it is the single most absolute boundary that exists anywhere in nature. A black hole is the densest thing the universe can make. It is the final rung in a very real sense, because it is mass that has won completely, mass with no size left at all, mass that has folded space and time around itself so tightly that it has sealed itself off from the rest of creation. And at the event horizon, the slowing of time that we've been chasing all night long finally reaches its destination. It does not slow by a third, as on the neutron star. it slows toward infinity. Let me show you what that strange phrase actually means, because it is one of the most haunting predictions in all of physics. Imagine you watched a friend, very brave and very foolish, fall slowly toward a black hole, with a bright clock strapped to their suit and a torch in their hand. As they drifted down toward the event horizon, you, watching safely from a distance, would see their clock begin to tick slower, and slower, and slower still. Their movements would seem to drag, as though the whole scene were being played back at falling speed. The light from their torch would stretch and redden and dim, and as they approached the horizon itself, from your point of view they would never quite reach it. They would appear to slow to a halt, hanging frozen just above the edge, the light from them fading until they simply faded from sight, suspended there, it would seem, forever. From where you float, your friend never actually crosses the line. They just freeze at the threshold and gently vanish into red. And yet, and this is the part that turns the whole thing into poetry, from your friend's own point of view, nothing strange happens at the boundary at all. Their clock ticks along quite normally. They sail across the event horizon in a perfectly ordinary moment, perhaps without even noticing the exact instant they cross the most important line in the universe. Two completely different stories, both entirely true, separated only by where each person stands in the slope of time. The faller crosses in a heartbeat, the watcher waits forever. That single difference, that gap between the one falling and the one watching, is the deepest thing that gravity does to time, and it sits at the heart of every black hole in the sky. Now, because human beings cannot resist a good rescue story, this is exactly the sort of place where our imaginations start to rebel. Surely you think, there must be some way to pull the falling friend back. If you had a strong enough cable, a powerful enough engine, a bright enough tractor beam out of the science fiction films, surely you could reach in and haul them out before they are lost. And the question of whether that is possible turns out to be one of the most clarifying things you can ask about a black hole. So let us ask it properly, with two famous stories to guide us. The first you may know. It is the film Interstellar, in which a crew flies close to an enormous black hole, and a single hour spent on a planet near its edge costs them 7 years of time back home. That is gravitational time dilation, the very effect we have been climbing toward all night, dramatized on the cinema screen. And the wonderful thing is that the filmmakers work closely with a real physicist, and the science underneath it is broadly sound. A single hour next to that black hole really could equal 7 years far away, a stretching of time by a factor of around 60,000. The only way that particular extreme is even theoretically possible is if the black hole is spinning very fast, which the one in the film is, and which let the writers get away with a number that would otherwise be impossible. So far, so faithful to reality. The second story is older and dustier and far less famous, and it is the one that lets us answer the rescue question head on. There was a science fiction television series around the turn of the millennium called Andromeda, and in its very first episode a great starship and its captain stray too close to a black hole and become trapped right at the edge, held there in what the show calls the time dilation field. To the captain, only a few seconds pass, but out in the wider universe, 300 years roll by while he hangs there, frozen at the threshold, until at last a passing salvage ship finds him, throws out cables, and tows him back out to safety, where he wakes barely older while everyone he ever knew has been dead for centuries. It is a wonderful premise, and it is also a perfect little laboratory for the physics. because the answer splits cleanly in two, and the difference between the two halves is the most important idea in this entire subject. Everything depends on one question. Had the ship truly crossed the event horizon, or was it merely sitting just outside it? If the ship had genuinely crossed the horizon, then no rescue is possible. None. Not with the strongest cable that could ever be woven, not with the most powerful engine that could ever be built, not with a tractor beam carrying all the energy in a galaxy, and not, as some people like to ask, by bringing a second black hole alongside to pull it back out. And the reason is the single most important thing to understand about a black hole, so let me say it as plainly as I can. Pulling something out from inside the horizon is impossible. It is not a question of needing more power. It is simply forbidden by the laws of the universe in the same deep way that travelling into yesterday is forbidden. Once you're inside the event horizon, the singularity lies in your future, the way tomorrow lies in yours, right now as you listen. You cannot steer away from tomorrow no matter how hard your engines burn, because it is not a place in space, it is a direction in time. Inside a black hole, every possible path you could take, every direction you could thrust, leads inward to the centre. There is no road out. Not because the road is long or steep, but because the road simply does not exist. A cable trying to haul you free would itself have to be pulled faster than light to do any good, and nothing can be pulled that fast. So the failure here is not one of strength. It is a failure of the very shape of reality. No amount of power turns a forbidden thing into a permitted one. But here is the lovely detail. The Andromeda story, perhaps by accident, actually describes the only version that could possibly be rescued at all. The ship is shown sitting on the edge in the time dilation field, and it is pulled out with cables. That is the picture of an object hovering just outside the horizon, not one that has fallen through. And for something that has not yet crossed the line, rescue is, in principle, allowed by the laws of physics. But, and this is a glorious but, the energy it would take is almost as absurd as the impossible case, and for a reason that is genuinely delicious once you see it. Remember that for 300 years to pass outside while only seconds pass on the ship, time on that ship has to be slowed by a factor of around 3 billion. And the only way to slow time that drastically without crossing the horizon is to hover unimaginably close to it. So close that the ship would have to hang at a height above the horizon thinner, in proportion, than the width of a single atom set against the whole black hole. And to hold a ship steady at a spot like that, fighting against a gravity that fierce, the force on the cable would be something like 100 billion times the pull of Earth's gravity. No cable made of any material, real or imagined, survives that for even an instant. It would not snap so much as evaporate. And the closer you crept to the horizon to get that dramatic time-freezing slowdown, the closer the energy required would climb toward infinity, which is the beautiful joke buried in the whole idea. The very thing that makes the story magical, the 3 centuries passing in a blink, is the exact same thing that makes the rescue impossible in practice. The drama and the impossibility are one and the same fact, wearing 2 different faces. And what of the idea of bringing a second black hole to pull the first one's prisoner free? It does not help in the slightest. A second black hole only adds more gravity to the situation, never less. Bring 2 black holes close together and their horizons do not cancel out or tug against each other in some helpful tug of war. They distort, they stretch, and eventually they merge into one larger black hole, and anything inside either of them stays inside the new combined one. The only thing that genuinely escapes a black hole, as far as we know, is a faint and ghostly trickle of radiation predicted by Stephen Hawking, leaking out so slowly that a single black hole would take vastly longer than the present age of the universe to fade away by it. That is not a tow line. That is a black hole quietly evaporating over a near eternity. So the rescue stays a dream, and the heaviest objects keep, forever, whatever falls past their edge. Which brings us at last to the very top of the ladder and to the largest and heaviest black holes of all. Because the ones we've been picturing, born from single, dying stars, weigh only a handful of suns. The lightest black hole ever found is just under 4 times the mass of the Sun. Those are the small ones, the local ones. But sitting at the centre of almost every large galaxy, including our own, is a black hole of a completely different order of magnitude. And these are the true giants of creation. At the heart of our own Milky Way, 27,000 light-years away through the crowded fields of stars, sits a black hole called Sagittarius A star. It weighs about 4 million times the mass of the Sun. 4 million suns, collapsed into a single point, anchoring the slow, majestic turning of our entire galaxy. For most of the night we've measured things against the Sun, but now even the Sun has become a small coin, and we are counting them out by the millions, and Sagittarius A star is, as these things go, a fairly modest example. In a galaxy called M87, some 55 million light-years away, there is a black hole weighing around 6.5 billion suns. That one made history a few years ago, when astronomers linked telescopes all across the Earth into a single planet-sized eye and captured the very first photograph ever taken of a black hole's shadow. A dark circle ringed by a halo of glowing, doomed light. We have an actual picture now. We looked into the abyss and we photographed the edge of it. But even 6.5 billion suns is not the end. There is an object called TON 618, a fierce and ancient beacon shining from more than 10 billion light-years away, so far that its light set out toward us when the universe itself was young. At its heart lies a black hole of around 66 billion times the mass of the Sun. 66 billion. To gather that much material, you could take every single star in our entire Milky Way galaxy, hundreds of billions of suns, crush them all together into one black hole, and you would still fall a few billion suns short of TON 618. It sits close to the very limit of how large astronomers think a black hole can possibly grow, and the discoveries keep coming. Only this past year, in the summer just gone, astronomers studying a distant galaxy known as the Cosmic Horseshoe, a galaxy so massive it visibly bends the light of things behind it into a glowing ring, announced a black hole of around 36 billion times the mass of the Sun. It may be the single most massive black hole ever measured, and it too sits near the theoretical ceiling of what the universe seems able to build. These are the ultramassive black holes, the heaviest individual objects in all of creation, the final and highest rung of our long climb. Now you might think that something this vast and heavy would tear any visitor to shreds long before they reach the edge. And for the small black holes, that is exactly true. Near a black hole only a few times the mass of the Sun, the gravity changes so sharply across even a short distance that anything falling in is stretched out into a long thin thread, an unpleasant fate that physicists with their gift for grim poetry actually call spaghettification. Your feet, being closer, would be pulled so much harder than your head that you would be drawn out into a strand of yourself. But here is the strange and counterintuitive gift of the giants. The bigger the black hole, the gentler the edge. A black hole of billions of suns is so enormous that its event horizon is a vast and gently curving boundary, larger across than our entire solar system. And near a horizon that huge, the gravity changes so smoothly from your head to your feet that you would feel almost nothing as you crossed it. You could drift over the event horizon of an ultramassive black hole completely intact, calm, unbroken, perhaps not even certain of the precise moment you had passed the point of no return, which means that the place where time slows toward infinity, the place we have been climbing toward all night long, is around these largest of all black holes, a place you could actually reach in one piece. You could sail right up to the edge of forever and step gently over it and never feel the door close behind you. From the outside you would simply slow and redden and fade and hang there at the threshold, while the rest of the universe ran on without you, for as long as the universe lasts. So let us stand here for a moment, at the top of the ladder we have climbed together, and look back down the whole length of it. We began with the sun, heavy beyond imagining, and yet barely able to bend time at all, losing only a few seconds a year, because all its mass was spread so wide and thin. We climbed the white dwarf, a sun crushed into an Earth, losing minutes. We reached the neutron star, a sun crushed into a city where time falls behind by nearly a third, and a spoonful weighs a mountain. We met the magnetar, the same crushing weight wrapped in the strongest magnetism in the cosmos. We found the overfed black widow, holding itself open at the very last instant before collapse. We paused at the enormous gentle giant of a star, 200 suns wide, and learned that it bends time hardly at all, because mass alone is never the point. And we arrived, finally, at the black holes, from the small and savage ones to the ultramassive lords at the centres of galaxies, where time at the edge slows not by a third, but toward forever. And running through all of it, from the first faint stumble of a clock on the sun to the frozen edge of a 66 billion sun abyss, there was only ever one quiet idea: take matter and crush it. The tighter you squeeze, the deeper the dent, and the deeper the dent, the more slowly time itself is willing to flow. Weight, it turns out, is really a kind of patience. The heaviest places in the universe are the places where time has almost stopped being in a hurry at all. There is something strangely comforting in that thought, when you let it settle over you in the dark. Out there, around those silent and titanic objects, are pockets of the cosmos where a single calm moment can outlast empires, where a heartbeat can stretch across the death of a star. The universe contains places where, if you could only reach them and survive, you could rest at the edge of one quiet instant while 300 years, or 300 million, washed by unnoticed. The heaviest things in all of creation are not really destroyers of time, they are its keepers. They gather it up, and they slow it down, and they hold it close, and they never let it go. The astronomers tell us too that this will not last forever, that even the ultra-massive black holes are creeping toward a kind of limit, and that in the unimaginably distant future, the great glowing quasars like TON 618 will quietly run out of material to feed on and wink out one by one into darkness and silence. The universe is still young enough that its heaviest hearts still blaze. We happen to be alive in the long, bright afternoon of all of this, able to look up and wonder and climb ladders like the one we climbed tonight, all the way from a spoonful of fallen starlight to the slowed and frozen edge of the deepest wells in existence. So let the weight of all of it rest gently on you now, the way sleep rests, slow and patient and unhurried. Somewhere far above the roof, a neutron star is spinning 700 times a second, and on its surface a clock is running a little behind ours, and it does not mind in the least. Somewhere a black hole the mass of 66 billion suns is holding a single instant open at its edge, and it will go on holding it long after this night, and you and I and everything we know have faded gently into the past. There is no hurry out there. There is all the time in the world and more pooled and slowed and kept safe in the heaviest places of the sky. You can let yourself drift now, somewhere in among them. Rest well, take care of yourself, and good night. As a child, you might have flipped through a magazine and just for a moment caught an article about a planet called Vulcan. Maybe it was a library book, or a lazy afternoon documentary murmuring in the background, one of those programs about the mysteries of the universe. You weren't really reading, you were a child, but a few words snagged and stayed with you, closer to the sun than Mercury. And that strange, final-sounding word, dissolved. Without a degree in astronomy, the best you could piece together was that there had once been a planet tucked between Mercury and the Sun, a world the solar system had somehow lost. And if you were old enough to have grown up counting 9 planets, all the way out to little Pluto, then this lost one made 10. 10 planets. And one of them simply gone. Then, years later, Pluto itself was quietly demoted, and even that number slipped through your fingers. And underneath all of it, half forgotten, a small question has been waiting patiently for you this whole time. Whatever happened to Vulcan? Tonight we're going to answer it, properly and completely, the way nobody quite managed when you were small. We'll go through the whole story, the bad news, the worst news, and yes, a little good news at the end, so settle in and get comfortable. Let yourself sink back into the pillow and drift along with a story that is more than 150 years old. A story about a planet that was named and celebrated and mourned and hunted across continents by some of the cleverest people who ever lived. By the time we reach the end of the night, I think you'll understand why so many brilliant minds believed in it, and where it should have been is, even now, one of the most quietly mysterious places in the entire solar system. If you enjoy drifting off to stories like this one, the slow, unfolding kind that ask big questions in a soft voice, you might think about subscribing, so the next story finds its way to you on some other sleepless night. A like or subscribe genuinely helps this channel more than you might think. Let's begin where every good ghost story begins, not with the ghost, but with the longing that conjured it. For as long as people have looked up and understood that the bright wanderers in the sky were other worlds, there's been a particular kind of restlessness about the space close to the sun. It is the hardest part of the sky to see. The sun is so overwhelmingly bright that anything orbiting near it is simply washed out, swallowed in glare, like trying to spot a candle held up in front of a searchlight. Mercury itself, the innermost planet we know, is famously difficult to catch. It hugs the sun so tightly that most people alive today have never knowingly seen it, even though it is right there, a naked eye planet, visible only in the brief bruised light just after sunset or just before dawn, low to the horizon, gone in minutes. There is an old story, almost certainly not true but too lovely to leave out, that the astronomer Nicholas Copernicus, the man who placed the sun at the centre of everything, died never having seen Mercury with his own eyes because the mists of the river near his home kept it hidden. Whether or not it really happened, the story tells you something true. The closer to the sun you look, the harder the looking becomes, and yet the human imagination does not like an empty space. If there is a region we cannot see into, we tend to fill it. From the early days of telescopes going right back to the 1600s, there were astronomers who suspected or hoped that there might be another world in there, hidden in the brightness, riding an orbit even tighter than Mercury's. Every so often, someone would report a small dark spot crossing the face of the sun, a tiny round shadow sliding over that blinding disk, and a thrill would go round. Was that it? Was that the hidden planet, caught at last in the act of passing between us and the sun? Almost always, the spot turned out to be something ordinary, a sunspot, one of those dark magnetic blemishes that come and go on the solar surface, or a small flaw, a fault in the telescope, a bird, a distant balloon. But the hope never fully died, it just waited. There is a particular way to catch a planet that orbits closer to the sun than we do, and it is worth understanding because it sits at the heart of everything that follows. When a world circles the sun on an orbit inside our own, every so often it passes directly between the Earth and the sun. We call that transit. The planet, lit from behind, becomes a perfect black dot, a small clean circle of darkness gliding slowly across the bright solar face over the course of a few hours. We see this happen with Mercury and with Venus, the two planets we know to be closer to the sun than we are. A transit of Venus is one of the great rare events in astronomy, something people once sailed to the far side of the world to witness. So the logic was simple and seductive. If there really were a planet inside Mercury's orbit, then one day, sooner or later, it too would have to transit. It would have to step in front of the sun and reveal itself as a small dark traveller. All anyone had to do was watch, patiently for long enough. And people did watch. There was a German pharmacist and amateur astronomer named Heinrich Schwabe, who, beginning in the 1820s, turned his telescope toward the sun on essentially every clear day for 17 years, partly in the hope of catching an inner planet in transit. He never found his planet. What he found instead, almost by accident, was that the number of sunspots rises and falls in a regular rhythm, a cycle lasting about 11 years, which turned out to be a genuinely important discovery about the sun itself. There is a small lesson tucked in there, and it will come back to us before the night is over. Sometimes you go looking for one thing, fail completely, and stumble into something far larger than the thing you were chasing. Across the Atlantic at Yale, a scientist named Edward Herrick set up his own careful watch, scanning the sun twice a day for any sign of the hidden world. He found nothing either. The space close to the sun kept its secrets, and the dream stayed a dream, formless and unproven. What that dream needed to become something more was a champion, someone respectable, someone with a towering reputation whose word carried the weight of certainty. And in the middle of the 1800s that someone arrived, and he was just about the most credible planet hunter the world had ever produced. To understand why everyone believed in Vulcan, you first have to understand the man who summoned it, because he was, at that moment, the man who had done the impossible once already. His name was Urbain Le Verrier, and he was French, born in 1811 in a town in Normandy, the son of an estate manager. He trained first in chemistry, then turned to the thing that would consume his life, which was celestial mechanics, the mathematics of how the planets move. It is a demanding, unglamorous discipline. It means taking the gravitational pull of every known body in the solar system and grinding through page after page of calculation by hand with a pen to predict exactly where each planet should be at any given moment. No computers, no calculators, just paper, ink, patience, and a mind that could hold an entire mechanical cosmos in its grip without dropping a single decimal place. Leverrier was extraordinarily good at it. He was also, by almost every account, extraordinarily difficult. Proud, sharp-tongued, impatient with people he considered slower than himself, which was nearly everyone. Years later, when he became director of the Paris Observatory, he ran it with such cold severity that much of his staff resigned in protest, and he was eventually forced out of the post, only to be reinstated some years afterward when his successor died. He was not a warm man, but he was a genius, and in 1846 he proved it in the most spectacular way imaginable. Here is what he did, and it really is one of the great triumphs in the history of science. There was a planet, Uranus, the outermost known world at the time, and it would not behave. It kept drifting away from where the equations said it should be, as though some invisible hand were tugging at it. A little ahead of schedule for a while, then a little behind. Most astronomers shrugged and assumed the data was simply imperfect. Leverrier did something bolder. He assumed the law of gravity was perfect, and that the wobble in Uranus must be caused by the pull of another planet, one nobody had ever seen lurking further out in the dark. And then he did the truly astonishing thing. Using nothing but the misbehavior of Uranus and the mathematics of gravity, he calculated where that unseen planet had to be. He worked out its position in the sky. He wrote it down, and he sent that prediction in a letter to an astronomer named Johann Galle at the Berlin Observatory, essentially saying, "Point your telescope here on this night and you will find a new world." Galle received the letter and pointed his telescope exactly where Leverrier had told him to, and there, within 1 degree of the predicted spot, almost close enough to touch, was a pale blue-green disk that no human eye had ever knowingly seen before. It was the planet we now call Neptune, a whole world found not by sweeping the sky and getting lucky, but conjured out of pure calculation, predicted on paper before anyone laid eyes on it. One of Leverrier's colleagues said that he had discovered a planet with the tip of his pen, without any instrument other than the sheer power of his arithmetic. Think about how that must have felt. To say, in effect, there is a world out there in the blackness. Here is exactly where it is. Go and look, and to be right. It made Leverrier instantly, overwhelmingly famous. It made him, in the eyes of Europe, something close to a prophet of the heavens. And it planted in his mind, and in the minds of everyone watching, a dangerous and intoxicating idea. If an unexplained wobble in one planet had revealed a hidden world once, then surely it could do so again. All you needed was another planet that misbehaved, and as it happened, Leverrier already knew of one, the smallest, fastest, most slippery of all the known worlds, Mercury. So now we come to the heart of the puzzle, the actual scientific problem that started everything, and I want to take it slowly because it is genuinely beautiful once you can see it clearly, and because almost nobody explains it properly to children flipping through magazines. Mercury, the innermost planet, loops round the Sun in just 88 days. Its orbit is not a perfect circle. no planet's orbit is. It is an ellipse, a slightly squashed circle, which means that as Mercury travels, it swings closer to the Sun, and then further away, closer and further, once per loop. The point on that orbit where Mercury comes nearest to the Sun has a name. It is called the perihelion, from the Greek, roughly, near the Sun. And here is the thing that turned out to matter so much. That nearest point does not stay still. With each orbit, the entire elliptical path of Mercury rotates very slowly, so that the perihelion, the point of closest approach, creeps a little further around the Sun each time. If you could draw Mercury's orbit over thousands of years and lay all the loops on top of one another, you would not see a single fixed ellipse. You would see a slowly turning flower, a rosette, each petal slightly rotated from the last, the whole pattern wheeling gradually around the Sun like the hand of an impossibly slow clock. Now, a turning orbit is not by itself mysterious. The astronomers of the 1800s understood perfectly well why it should happen. Mercury does not orbit the Sun alone. It is tugged gently but constantly by the gravity of all the other planets, by Venus and the Earth, and mighty Jupiter further out, and all those little tugs add up, and they make Mercury's orbit slowly rotate. The mathematicians could calculate exactly how much rotation all those planetary tugs should produce. And this is where it gets interesting. When they did the calculation with all the care in the world, and then compared it to what Mercury actually does, the numbers did not quite match. Mercury's orbit was turning slightly faster than it had any right to. There was an extra little push, a small surplus of rotation that the known planets could not account for, no matter how carefully you added up their pulls. The size of that leftover, in the end, came out to about 43 seconds of arc per century. I should pause on that number, because it sounds like nothing, and in a sense it is almost nothing. A second of arc is a unit of angle so tiny it strains the imagination. There are 60 seconds of arc in a minute of arc, and 60 minutes of arc in a single degree, and 360 degrees in the whole circle of the sky. So a second of arc is 1/3600th of 1 degree. 43 of them is the width of a small coin seen from several kilometers away. And per century, remember? This was a discrepancy that took 100 years to add up to that whisker of an angle. It is a measure of how exquisitely precise astronomy had become that anyone could even notice such a thing, let alone be bothered by it. But notice it they did. And to a mind like Leverrier's, that tiny, stubborn, unexplained surplus was not a rounding error to be waved away. It was a crack in the perfect machine of the heavens, and cracks, in his experience, had hidden worlds behind them. He had been here before, an unexplained tug on a planet. Last time the answer had been Neptune, a real world found exactly where his mathematics said it would be. So he reasoned, with the full confidence of a man who had already pulled this exact trick once, that the surplus in Mercury must mean the same thing. There must be something else in there, something close to the Sun, pulling on Mercury, something nobody had yet seen because it was lost in the glare. Perhaps a single planet, smaller than Mercury, riding a tight hot orbit nearer to the fire, or perhaps a swarm, a belt of small bodies too faint to spot individually. Either way, there was unseen mass down there near the Sun, and it was leaving its fingerprints on Mercury's orbit. And this time, before he had found anything at all, before a single confirmed observation, Leverrier did something that tells you everything about his confidence. He gave the planet a name. He called it Vulcan. after the Roman god of fire, the blacksmith of the gods, who laboured at his forge deep in the heat of the earth. It was a fitting name for a world that would have to endure the ferocity of the near sun, scorched and blazing, the closest planet to the furnace. The name was perfect, the reasoning was sound. The man making the claim was the most successful planet hunter in human history. The solar system, it seemed, was simply waiting to hand over one more secret. All that remained was for anyone to actually see the thing. And then, on the very last day of 1859, a letter arrived in Paris that seemed to deliver exactly that. It came from a man almost comically unlike Leverrier. His name was Edmond Modeste de Lescarbot, and he was a country doctor in a small village called Orgères-en-Beauce, out among the wheat fields some 70 kilometres southwest of Paris. He was a gentle, modest, retiring sort of man, a physician who tended the ordinary aches and fevers of rural life, and who, in his spare hours, had built himself a little observatory beside his house and fitted it with a small telescope, a refractor not much more than 9 centimetres across. He was, in other words, an amateur, a hobbyist. The kind of person the lordly director of the Paris Observatory would not normally cross the street to speak to. But this country doctor had a story to tell. He wrote that on an afternoon the previous spring, on the 26th of March, he had been at his telescope, watching the sun, as was his habit. It was one of those warm afternoons on the edge of spring. The flow of patients had eased, and he had slipped out to his little observatory to look. And as he watched the bright disk of the sun, a small, round, perfectly dark spot came into view near its edge. At first he thought little of it, but after some time he realised with a jolt that it was moving. Slowly, steadily, the little black dot was crawling across the face of the sun. He'd seen the transit of Mercury once before, years earlier, and this looked just like it, only smaller. A tiny dark traveller, sliding over the solar disk. He scrambled to measure it, to time it, scratching his numbers with a piece of charcoal onto a wooden board there in the observatory, because that was what he had to hand. And then, in the middle of this once-in-a-lifetime observation, a patient arrived at his door, and the country doctor, being a country doctor, had to pull his eye from the telescope and go and tend to them. By all accounts, he estimated the little spot took something over an hour to make its way across, and then it slipped off the far edge of the sun and was gone. For 9 long months, Lescarbot told almost no one. He was a modest man, unsure of himself, half afraid he'd made a fool's mistake. But he'd heard of the great Leverrier's idea, the famous theory of a hidden planet near the sun, and slowly the conviction grew in him that what he had seen that spring afternoon might be the very thing the great man was looking for. So at last he gathered his courage and wrote his letter, and he entrusted it to a passing acquaintance, a local inspector of roads and bridges, to carry toward Paris and deliver into the proper hands. And so, on the final days of the year, the letter reached Urbain Le Verrier. Now, you might imagine the famous astronomer would have been delighted, even grateful. He was neither, at least not at first. His reaction was suspicion. Who was this provincial nobody, this rural doctor with his homemade telescope, claiming to have plucked the prize that the professionals had hunted for in vain, and worse, claiming to have seen it 9 whole months ago and said nothing until now? Le Verrier did not write a polite reply. He decided he would go to Orgères himself, in person, unannounced, and put the doctor to the test. He was supposed to be travelling to his father-in-law's home for a New Year celebration, but the train timetables he worked out just barely allowed him to make the journey to the village and back. So he commandeered a companion to come along as a witness, climbed aboard a train, and set off into the countryside to corner Edmond Lescarbot in his own home. The scene that followed has come down to us through the years, and it is one of the small, perfect set pieces of scientific history. Picture the contrast. On one side, the timid country doctor, small and simple and nervous, suddenly confronted in his own modest observatory by the most celebrated astronomer in France. On the other, Leverrier, tall, imperious, cold, his reputation preceding him like a thundercloud, in absolutely no mood to be charmed. He did not begin with pleasantries. According to the account that survives, he drew himself up to his full height and addressed the trembling doctor with something close to a threat. "It is then you, sir," he said, "who claim to have observed the planet inside Mercury's orbit, and who have committed the grave offence of keeping your observation secret for 9 months. I have come," he went on, "with the intention of doing justice to your claims, and of demonstrating either that you have been dishonest, or that you have been deceived." Imagine being on the receiving end of that. A quiet man who tends to sniffles and broken bones, ambushed in his garden shed of an observatory by a national hero who has just told him, to his face, that he is here to prove him either a liar or a fool. And yet Lescarbot held up. He showed Leverrier his little telescope. He explained in patient detail how he had made his measurements, how he had timed the transit, how he'd worked out the figures, even the humble charcoal scratchings on the wooden board. He answered every sharp question, and slowly, grudgingly, the great man's suspicion gave way. By the end of that strange winter interview, Leverrier had convinced himself that this gentle provincial doctor was neither dishonest nor deceived, but had genuinely seen what he claimed to have seen. He even carried away the wooden board with its charcoal calculations, and would later present it, this humble plank, to the Academy of Sciences in Paris as a kind of relic of the discovery, the board on which a country doctor had recorded the arrival of a new world, and so Leverrier announced it. In the first days of 1860, before the Academy of Sciences, the most respected scientific body in France, he declared that the hidden planet inside Mercury's orbit had been found. He gave it the name he had chosen long before, Vulcan. He even worked out from Lescarbot's measurements the details of its orbit. He calculated that Vulcan circled the Sun once every 19 or 20 days, at a distance roughly a third of Mercury's, deep in the searing brightness near the fire. The little country doctor was lifted almost overnight from total obscurity to national fame. He was awarded the Legion of Honor, France's highest decoration, and was suddenly invited to address learned societies, the modest physician who had caught the planet the great Leverrier had predicted. For a brief, shining moment, the story was complete. The mathematics had foretold a world. An honest observer had seen it. The greatest planet hunter alive had confirmed it and named it. The solar system had a new member, scorched and secret, riding close to the sun. The crack in the heavens was sealed. It was, of course, too good to be true. And here, my friend, is where the bad news begins in earnest. Because almost at once the trouble started. It began quietly, with a few uncomfortable questions from other astronomers, the kind of questions that are easy to ignore when you very much want a thing to be true. The first problem was one of size. From the measurements, the little object Lescarbot had seen was tiny. The estimates suggested it had only a small fraction of Mercury's mass, less even than our own moon. And that created a real difficulty, because the whole point of Vulcan, its entire reason for being invented, was to explain that stubborn surplus in Mercury's orbit. But a body that small, that faint, that feather-light, simply could not tug hard enough to do the job. It was far too little to account for the wobble it was supposed to cause, so even if Lescarbot really had seen a planet, it was the wrong planet. It could not be the answer. And then came the second, sharper problem. If there really were a planet down there big enough and bright enough for a country doctor to catch with a small telescope, then other, better-equipped astronomers with finer instruments and clearer skies ought to have seen it too. And here the silence began to grow deafening. One astronomer, observing from Brazil with a telescope considerably more powerful than Lescarbot's, had been watching the sun at around the very time the doctor claimed his transit took place. He had seen nothing at all, no dark dot, no traveller, an empty, untroubled solar disk. That was hard to explain away. If Vulcan had truly been crossing the sun that afternoon, how could a sharper eye with a better telescope have missed it entirely? The most likely truth, the one that history has settled on, is gentle and a little sad. Lescarbot was almost certainly an honest man who made an honest mistake. What he probably saw that warm spring afternoon was a sunspot. One of those dark magnetic patches that drift across the sun's surface, exactly the sort of thing that fooled so many hopeful watchers before him. A sunspot can look round and dark and well-defined, and over hours it does appear to move, carried along as the sun rotates. To an eager amateur who knew that the famous Leverrier was hunting for just such a dark spot, a sunspot might have looked very much like a dream coming true. He saw what he hoped to see. It is one of the oldest and most human of all mistakes, and it has caught far greater observers than a country doctor in a village among the wheat fields. But here is the thing about a beautiful idea backed by a powerful man. It does not die just because the first piece of evidence crumbles. By now, Vulcan had a name, an orbit, a discovery story, and the endorsement of the most famous astronomer in the world. It had momentum. And so, rather than fading away, the planet entered a strange and febrile new phase of its life, a phase that would last for decades. Word had gone out that there was a planet to be found near the sun, and suddenly, all over the world, people began to find it. This is the part of the story that is almost comic and also a little haunting. Once everyone knew to look for a dark spot near the sun, reports of dark spots near the sun came flooding in. An observer in London saw one, another in Manchester backed up by a colleague, one in Istanbul. Sightings arrived from amateurs and professionals alike, each one a small dark object near the sun, each one breathlessly offered up as Vulcan caught in the act. From these scattered reports, mathematicians tried to pin down the planet's orbit, and they came up with answers. Periods of 17 days, of 19 days, confident numbers built on a foundation of fog. Leverrier himself spent years of his life chasing it, gathering every report, adjusting and readjusting his calculations for Vulcan's orbit as each new sighting came in, like a man constantly redrawing a map of a country that kept moving. Every so often he would use his latest figures to predict a date when Vulcan should next transit the sun, a day when, if his calculations were right, the little planet would step in front of the fire and reveal itself to all the watching telescopes of the world, and astronomers would prepare and wait and watch on the appointed day. and nothing would come. The sun would cross the sky, serene and empty, and Vulcan would not appear. And Leverrier would gather himself and adjust his figures once more and name another date, and that one too would pass in silence. It is hard not to feel for him. This was the man who had found Neptune with the tip of his pen, who had reached into the darkness with nothing but mathematics and pulled out a world. Of course he believed he could do it again. Of course every failed prediction looked to him like a problem of detail, a small error in the orbit to be corrected, rather than a sign that the planet had never been there at all. He went on believing and adjusting and predicting year after year, and in 1877 Urbain Le Verrier died in Paris at the age of 66, still convinced that somewhere in the glare near the sun his Vulcan was waiting to be properly caught. He was buried in the great Montparnasse cemetery, honoured as one of the giants of French science, which he truly was. His likeness would one day appear on a French banknote. He had discovered one planet by pure reason, an achievement so dazzling it has never really been equalled, and he went to his grave chasing a second one that did not exist. There is something almost unbearably human in that. The same boldness, the same unshakable faith in his own calculations gave him both his greatest triumph and his longest, saddest mistake. He simply could not tell from the inside which was which. But the death of Leverrier did not kill Vulcan. If anything, the planet's most dramatic chapter was still to come, and it unfolded not in the salons of Paris, but out on the wild frontier of the American West, under a sky about to go dark in the middle of the day. Because there was one circumstance, one rare and spectacular circumstance, in which a planet hiding near the sun might be caught even without a transit: a total eclipse of the sun. When the moon slides perfectly in front of the sun and blots it out completely, the dazzling disk is hidden, and for a precious couple of minutes the sky around the sun goes dark, dark enough that stars and planets normally drowned in daylight blaze suddenly slide into view. And in that brief, unnatural twilight, the reasoning went, if there really were a planet riding close to the sun, it ought to shine out, right there beside the blacked out disk, finally visible, finally undeniable. All you had to do was be standing in the path of a total eclipse, with a telescope ready in those 2 fleeting minutes of darkness, and sweep the space around the sun, and there it would be. In the summer of 1878, the path of just such a total eclipse swept across the western United States, cutting down through the territories and young states of the Rocky Mountains. And it drew to the dusty frontier towns along its path an extraordinary gathering of scientists, racing west by railroad to plant their telescopes in the high desert and meet the moon's shadow. It was, in its way, a carnival of science on the edge of the wilderness. Frontier towns that existed only because the railroad passed through them, places of windswept prairie and little else, suddenly filled with the most distinguished astronomers of the age, unpacking precious instruments, watched with friendly bemusement by the local residents, who had never seen anything like it, and who, by all accounts, treated their strange learned visitors with great kindness. Among the people drawn west by that eclipse was a cast of characters worthy of a novel. Therefore a young inventor named Thomas Edison, already famous for the phonograph, who had come out to the frontier to test a delicate device of his own making, a heat-measuring instrument he called a tessimeter, with which he hoped to detect the faint warmth of the sun's outer atmosphere. He set it up in a henhouse, by some accounts, and the day before the eclipse he tried it on a bright star, and during the eclipse itself the gadget proved almost too sensitive for its own good, and did not quite work as he had hoped. The very day after he returned home from this adventure, Edison began the work that would lead him to the electric light bulb, but that is another story. There was also a remarkable woman named Maria Mitchell, the most famous female astronomer in America, who led an expedition of women out to the eclipse path in part to demonstrate, in an age that doubted it, that women belonged in science every bit as much as men. There were photographers ready to capture the sun's ghostly outer halo, its corona, for the historical record. And then there was the man at the centre of our story that day, an astronomer named James Craig Watson. Watson was no amateur dreamer. He was one of the most respected observers in America, a professor who had already discovered more than 20 asteroids, faint specks of rock that he had teased out of the crowded sky by sheer skill and persistence. He had been called the brightest son of his university. If anyone alive had the sharp eyes and the disciplined mind to catch a difficult object near the sun, it was Watson. And he had come to Wyoming for one purpose above all others. He had come to find Vulcan. He set himself up with his telescope and his hand-drawn charts of the stars that ought to be near the sun, so that if he saw anything that was not on his charts, anything that did not belong, he would know he had found a new world. The day of the eclipse arrived. The light began to fail as the moon crept across the sun. And then came the moment of totality, that strange and overwhelming experience when the last sliver of sun vanishes and the world plunges into an eerie midday dusk, the temperature dropping, the birds falling silent, the corona flaring out around the black disk of the moon like a crown of pale fire. Watson had only a couple of minutes. He began to sweep the sky beside the sun, east and west, scanning for anything out of place, and there, in that brief and electric darkness, he saw it, a small object, glowing with what he later described as a dull, muddy light, sitting in the sky near the sun, in a spot where his chart said no known object should be. He measured its position as quickly as he could before the daylight came flooding back. He was certain he had done it. After all the failed transits, all the empty predictions, the elusive planet had shown itself at last, in the one circumstance where it could not hide, and a sober, brilliant, experienced astronomer had seen it with his own eyes and written down where it was, and he was not alone. Another seasoned observer at the same eclipse, a man named Lewis Swift, also reported seeing a strange object near the sun that did not match any known object. Two respected witnesses, two independent sightings. For a few heady weeks it seemed that Vulcan had finally decisively been caught. And yet, you can feel the "and yet" coming by now, can't you? Because this is the bad news, and the bad news in this story is patient and relentless. When astronomers carefully compared the positions that Watson and Swift had recorded and checked them against detailed star charts, the magic began to drain away. The objects they had seen could be explained, uncomfortably but plausibly, as ordinary stars, known stars that happened to lie near the sun's position in the sky that day. Stars that, in the rush and dazzle and pressure of those 2 precious minutes, with the daylight about to return, had been slightly misplaced or misidentified. It is no insult to Watson or Swift to say so. Observing during a total eclipse is fiercely difficult. You have moments, not minutes. Your heart is pounding. The light is doing impossible things, and you're trying to make precise measurements of faint points of light against a sky that is behaving like nothing you have ever seen. The most likely explanation, the one the wider community of astronomers slowly and reluctantly came to accept, was that the Great Vulcan sighting of 1878 was once again a case of seeing what one desperately hoped to see. Watson himself never accepted it. Like Leverrier before him, he held on to his Vulcan to the end. He was so convinced of what he had seen that he set about building a special underground observatory, a sunken chamber from which, he believed, the deep shadow might let him glimpse stars and perhaps even Vulcan in broad daylight, so that he could prove the planet was there for all to see. He did not get the chance to finish that work. He died not long after, in 1880, still a believer, still certain that a small muddy point of light he had caught in 2 minutes of eclipse darkness was a world that history would one day vindicate. And so the decades wore on, and the pattern simply repeated, growing wearier each time. A new eclipse, a fresh band of hopeful astronomers, a careful sweep of the darkened sky beside the sun, and nothing. No muddy light, no dark traveller, no planet. The greatest observers of the late 1800s turned their finest instruments on the space inside Mercury's orbit again and again, and that space gave up nothing at all. Slowly, painfully, the mood among astronomers shifted from excitement to doubt to a kind of embarrassed resignation. The planet that the immortal Leverrier had named, that a humble doctor had been decorated for finding, that a brilliant American had staked his reputation on glimpsing, would not show itself because, the suspicion grew, there was simply nothing there to show. By the early years of the 20th century, most serious astronomers had quietly given up on Vulcan. It had become an awkward ghost, a planet that lingered in the textbooks and the popular imagination, in the half-read magazine articles and the murmured documentaries, long after the experts had stopped believing in it. But notice, if you will, what had and had not been settled. Everyone had given up on finding the planet. Nobody had explained the thing that started it all. Mercury's orbit was still turning too fast. That stubborn surplus of 43 seconds of arc per century was still there, still real, still entirely unaccounted for. The detective's chief suspect had been cleared, but the crime remained. Something was making Mercury misbehave, and now there was no hidden planet to blame. And so the puzzle that had haunted astronomy for half a century passed, unsolved, into a new century, waiting for a completely different kind of mind to look at it in a completely different way. That mind was about to arrive, and here at last we turn the corner from the bad news into the worse news, and then, if you stay with me, into something rather wonderful. To get there, we have to leave the world of telescopes and eclipses and frontier towns entirely, and step into the mind of a young man working, of all places, in a patent office, and then in the quiet studies of European universities, a man who was about to look at Mercury's stubborn little wobble and see in it, not a missing planet, but a missing piece of reality itself. His name, of course, was Albert Einstein, and what he was building slowly and painfully over about a decade was an entirely new understanding of gravity. For more than 200 years, ever since Isaac Newton, gravity had been understood as a force, an invisible pull that reached across space between any two objects, the sun pulling on Mercury, the Earth pulling on the Moon, a tug at a distance. Newton's picture was magnificent, and it worked superbly well, well enough to find Neptune, well enough to send spacecraft across the solar system even today. But Einstein came to believe that the picture was, at its deepest level, not quite right. Gravity, he proposed, was not a force pulling across empty space at all. It was something far stranger and more beautiful. It was the bending of space and time themselves. Here is the idea, as gently as I can give it to you in the dark. Imagine that space is not just emptiness, a passive stage on which the planets move. Imagine instead that space, woven together with time into a single fabric, can be curved and shaped like the surface of something flexible and smooth. And imagine that anything with mass, anything heavy, presses into that fabric and creates a kind of dip, a curved valley around itself. The more massive the object, the deeper the dip. The sun, enormously heavy, sits in a deep well of curved space-time, and the planets, including Mercury, are not being pulled by a mysterious invisible rope. They are simply rolling along the curved landscape, following the natural contours of the warped space around the sun, the way a marble would circle around and around the inside of a smooth bowl. Gravity, in Einstein's vision, is not a force. It is the shape of space telling matter how to move. There is a famous way of summing it up. Matter tells space how to curve, and curved space tells matter how to move. And now comes the moment, the real climax of our entire story, and I want to slow right down for it, because it is one of the most thrilling moments in the history of human thought, and it happened in the quiet of a study, on paper, with a pen, much like Leverrier's Neptune, but reaching far deeper. In the autumn of 1915, Einstein had his new equations of gravity nearly in their final form, and he realized that he could test them on an old, famous, unsolved problem, the orbit of Mercury. He could take his new picture of curved space-time, work out exactly how a planet should move through the steep warped space close to the Sun, and see whether his theory predicted any extra turning of Mercury's orbit, any surplus beyond what Newton and the other planets could explain. He sat down and he did the calculation. And out of the mathematics, out of the pure geometry of curved space-time near the Sun, there emerged a number, an extra advance in Mercury's perihelion. 43 seconds of arc per century. 43, the exact figure, the very surplus that had haunted astronomy for over half a century, the discrepancy that had launched 1,000 fruitless searches, that had conjured a phantom planet and decorated a country doctor, and sent astronomers racing to the frontier and broken brilliant men against the glare of the sun. It fell straight out of Einstein's new theory of gravity, not as a guess, not as something he had put in by hand, but as an inevitable consequence of the way space itself curves around a massive body. He had not gone looking for Mercury's wobble. The wobble had simply appeared of its own accord the moment his equations were complete, like a signature confirming that the whole strange edifice was true. Einstein later said that when he saw that number come out of his equations, he was so overcome that he felt his heart actually racing in his chest, palpitations as though something inside him had snapped loose. One of his biographers called it the single strongest emotional experience of Einstein's entire scientific life, perhaps of his whole life, and you can understand why. In that instant, he was not merely solving an old astronomical puzzle. He was receiving the first hard proof that his radical, almost unbelievable new vision of reality, the bending of space and time, was actually how the universe worked. Mercury's tiny, stubborn, century-old wobble was the cosmos whispering back to him, "Yes, you have understood me correctly." And do you see what that meant for Vulcan? Do you see the quiet, gorgeous mercy of it? There was no missing planet, because there had never needed to be one. Mercury's orbit was turning too fast by exactly 43 seconds of arc per century, not because some hidden world near the Sun was tugging at it, but because Mercury moves through the steeply curved space-time close to the Sun, and that curvature, all by itself, makes its orbit slowly wheel around. The surplus was not the fingerprint of an unseen planet. It was the fingerprint of gravity's true nature. The crack in the heavens that Leverrier had spotted was real. He had simply misread what lay behind it. He thought he was looking at the shadow of a hidden world. He was actually looking, without knowing it, at the first faint evidence that space and time can bend. He was standing at the doorway of the deepest idea in modern physics, and he mistook it for the doorway of a small hot planet. Vulcan was never a world. Vulcan was a misunderstanding of something far, far grander than any world. This is why I told you, at the very start, that the bad news and the worst news would turn, in the end, into something wonderful. Because the failure to find Vulcan was not an embarrassment to be swept under the rug. It was one of the great clues. The empty space where the planet should have been was not really empty. It was full of curved space-time, full of the proof of a new universe, waiting for someone with the right eyes to read it. Every astronomer who looked and found nothing was, without knowing it, helping to clear the way for the truth. The nothing they kept finding was the answer, and what an answer it turned out to be. Because Einstein's theory of gravity, the same theory that dissolved Vulcan with a single number, did not stop at Mercury. It went on to reshape our entire understanding of the cosmos, and nearly everything we now know about the universe at its grandest scales flows from it. A few years after Mercury, in 1919, astronomers tested another of Einstein's predictions during a total eclipse, the very kind of eclipse that Vulcan's hunters had once haunted. The theory said that the Sun's curved space-time should bend the path of starlight passing near it, shifting the apparent positions of stars seen close to the eclipsed Sun. The astronomers measured it, and the starlight had bent by just the amount Einstein had foretold. The same curved space that turned Mercury's orbit was caught in the act of bending light itself. Einstein woke up, more or less, to find himself the most famous scientist on Earth, and it kept unfolding. That theory of curved space-time is the reason we understand black holes, those places where space and time are bent so steeply that not even light can climb back out. In fact, the very first exact solution describing a black hole was worked out by a physicist named Carl Schwarzschild, who solved Einstein's equations while serving in the trenches of a war, sending his calculations back from the front, and who died of illness only months later. From Mercury's quiet wobble had come the mathematics of the most extreme objects in existence. That same theory tells us that the entire universe is expanding, that space itself has been stretching outward since the beginning of time. It predicted ripples in space-time gravitational waves set off by colliding black holes far across the cosmos, ripples so faint that it took a century and the most sensitive instruments ever built to finally catch one washing over the Earth. And in a much humbler and more everyday way, that same understanding of how gravity bends time is the reason the navigation system in your phone works at all. The satellites overhead, sitting higher up in the Sun and Earth's gravity, experience time running very slightly differently than we do down here, and unless engineers correct for that tiny difference, every map would drift off by kilometers within a day. Every time you find your way with a glowing dot on a screen, you're quietly relying on the same physics that erased the planet Vulcan. The curve of space and time is not an abstraction. It is woven through your ordinary life. So here is where we have come to. The planet you half remembered, the lost world between Mercury and the Sun, was never there. That is true, and there is no softening it. But the reason it was never there is that the space it was supposed to occupy turned out to be filled with something deeper than any planet. The bending of reality itself, the clue that led us to black holes and gravitational waves in the expanding universe, and the satellites that guide you home. Vulcan did not simply vanish into nothing. It dissolved, as that old magazine article so strangely put it, and what it dissolved into was a truer and stranger and more magnificent picture of the cosmos than the people who first dreamed it could ever have imagined. If you're going to lose a planet, that is about the most beautiful way there is to lose one. Even though it seems the question of Vulcan had been put to rest, there were still hopefuls through the 20th century looking for something similar. When astronomers finally let go of Vulcan as a planet, a smaller and more modest version of the dream lingered on. Perhaps, they thought, there was no single world down there, but there might still be something. A scattering of small bodies, asteroids, little chunks of rock too tiny ever to have explained Mercury's wobble, but real nonetheless, riding in the gravitationally calm zone between Mercury and the Sun. These hypothetical objects even got a name of their own, drawn from the old ghost. They are called the Vulcanoids, and in principle there is room for them. Calculations show a genuine stable band, very roughly between a 15th and a 5th of the Earth's distance from the Sun, where small objects could in theory survive on quiet orbits without being flung away or swallowed. So the hunt in a gentler form went on. And it has been a thorough hunt. Astronomers have searched for Vulcanoids during total eclipses in those same dark minutes that once tempted Watson. They have used special cameras carried up high in aircraft, above most of the murk of the atmosphere, to scan the twilight sky close to the Sun. They have turned space-based observatories, instruments designed to stare at the Sun and its surroundings without an atmosphere in the way, onto the problem, and they have combed through their images looking for any small moving speck. When the spacecraft Messenger journeyed to Mercury and settled into its long study of that scorched little planet, it too kept watch, using its closest approaches to the Sun to look for any Vulcanoids that might be lurking nearby. And after all of that searching, with all of those instruments, the result so far is the same answer that the Sun has been patiently giving for 150 years. Nothing. No Vulcanoids have ever been confirmed. The searches have grown so sensitive that we can now say with some confidence that if anything is down there at all, it must be small, just a handful of kilometers across at most, and there can be very few of them. The calculations even suggest that any such objects, ground down by endless collisions and nudged by the subtle pressure of sunlight over the long ages, would mostly have been cleared out within the first billion years or so of the solar system's life. So even the modest dream, the dream of a few quiet rocks, appears to be very nearly empty. The space close to the Sun seems once again to be guarding its emptiness. But, and this is the last and best but of the night, the very same region that refuses to hold a planet or even a swarm of rocks has handed us a brand new puzzle, one that scientists are genuinely chewing on right now, and it whispers faintly of lost worlds after all. Because Mercury itself is strange. deeply, unexpectedly strange. When we measure Mercury carefully, we find that it is far too dense for its size. Buried inside that small planet is an enormous iron core, taking up most of the world, wrapped in only a thin shell of rock, as though Mercury were the stripped-down metal heart of something that was once much larger. One leading idea to explain this is dramatic. Perhaps the young Mercury was struck a colossal blow, an impact so violent that it tore away most of its rocky outer layers and flung them into space, leaving behind mostly the dense metal core we see today. If that is what happened, then Mercury is a survivor, a scarred remnant of some early catastrophe near the Sun. I want to be clear and honest with you here, because that matters in a story all about people believing too easily. This giant impact idea is one hypothesis among several, not a settled fact. We do not know for certain why Mercury is so iron-rich, but it is a serious and widely discussed possibility, and it hints that the inner solar system may once have been a far more crowded and violent place than the calm arrangement we see now. And there is more, and it deepens the mystery in a lovely way. When we look out at the thousands of planets we've now discovered circling other stars, we find something that ought to puzzle us about our own home. Around a great many other stars, planets crowd in close, closer to their suns than Mercury is to ours, sometimes several of them packed into that hot inner region. Tightly bunched inner worlds turn out to be common across the galaxy, and yet our own solar system has nothing at all inside Mercury's orbit. That inner space, the very region where Vulcan was supposed to live, is conspicuously unusually bare. Why? Why should our inner solar system be so empty when so many others are full? Scientists do not have a settled answer, and one of the genuine possibilities they consider, carefully and seriously, is that our solar system may once have had more worlds in close to the Sun. A generation of inner planets that were lost long ago, either ground up in collisions with one another or swept inward and swallowed by the young Sun, leaving Mercury as the last battered survivor of a vanished inner family. I will say it plainly once more, because honesty is the whole point of this story. This is informed speculation, not proven history. We have no fossil of a lost inner world, no smoking gun. But the questions are real, and they are being asked by serious people with serious instruments right now. And is that not a quietly astonishing place to arrive? You started the night mourning a single lost planet, a childhood ghost named Vulcan that turned out never to have existed, at least during the recent life of Mercury. And here at the end, science hands you something gentler and stranger in its place. Not the planet you were promised, no, but a real and open question about whether the space near the Sun, the very space where you imagined your lost world, might once have held worlds after all. Worlds that truly came and went before any human looked up to count them. The old dream was wrong in its details, wrong in its name and its orbit and its 43 seconds of arc. But the deep intuition underneath it, the feeling that the bright, fierce region close to the Sun is a place of secrets, a place where something might have been lost, that intuition was never entirely foolish. It just had to wait a very long time and travel through general relativity and exploding stars and other suns to find its truer shape. So if a small part of you has carried that childhood question all these years, that quiet wondering about the lost planet between Mercury and the Sun, you can let it rest now. You did not misremember a real world into nothing. You remembered faintly the edge of one of the greatest stories in all of science, a story about how we reach into the dark with our imperfect minds and get it gloriously wrong, and in getting it wrong, stumble into something truer than we ever dreamed. Vulcan was never a planet, in the 19th century at least, but it was never nothing. It was a question the universe asked us, and the answer turned out to be the shape of space itself. And if we do find evidence that there had indeed been planets between Mercury and the Sun, perhaps millions or even billions of years ago, then perhaps they will need names, and perhaps you have at least one name picked out already. For now, there is only the soft curve of space-time near a star, and a long human story of looking and longing and finally, beautifully understanding. Rest easy. The solar system is exactly as full as it should be, and the empty place near the Sun is not empty at all. It is simply full of something we had to grow up as a species to be able to see. Sleep well. The Sun will rise in the morning on its gently curving path through space, exactly where it should be. And the question some of you have carried for so long can finally close its eyes tonight too. Good night. Somewhere on Mars, in a wide and ancient crater, the air is doing something it should not be able to do. A faint trace of gas seeps up out of the cold ground, rises through the thin pink atmosphere, and then, within hours, simply vanishes again. You would never catch it with your eyes. It is invisible, it has no smell, and it is present in amounts so small that you could gather the entire supply hanging over a whole crater into a few cupped handfuls of air. And yet, it should not be there at all. The gas is methane. Here on Earth, almost every single molecule of it is made by something that is alive. Cattle and swamps, deep ocean microbes, the quiet bacteria living inside your own body. Life breathes out methane the way you breathe out the warmth of a sigh on a cold night. And if you're sure you've smelled it, that sharp rotten egg tang of a gas leak, the smell is not actually the methane. Gas companies add a trace of a sulfur compound called mercaptan on purpose, precisely so a leak you could never otherwise notice will reach your nose in time. So when a small nuclear-powered rover, sitting alone on the floor of a Martian crater, drew in the air around itself and tasted methane, and then watched it rise with the seasons and fade away again, a soft alarm began to sound in laboratories all across our world. Because methane on Mars should not last. Sunlight tears it apart within a few centuries, which is the blink of an eye on a planet billions of years old. If the gas is there at all, then something has to be making it now. Not long ago, now, today. Somewhere beneath that rusted surface, something is topping the supply back up. And here is the part that keeps the question awake long after the lights go out. A second spacecraft circling high above the planet, carrying instruments far more delicate than anything down on the ground, went hunting for that same methane across the entire globe. And it found nothing, not a whisper. One machine on the surface says the gas is real. Another machine in orbit says it cannot possibly be. Both of them are ours. Both of them are extraordinarily good at what they do, and they cannot both be right. So tonight, let us take the oldest question we have ever aimed at another world, and let us ask it gently and honestly, without reaching for the easy answers that have fooled us so many times before. Is anything actually alive on Mars right now? If that question stirs the same quiet thrill in you that it does in me, and if you would like to drift off to more long, calm journeys through real science, the kind made to be listened to in the dark, then take a small moment now, before we travel any further, to follow along by subscribing. It simply helps these slow nighttime documentaries find their way to other curious minds who cannot sleep. And then we can settle in together properly. Comfortable? Good. Then let us begin where every honest answer about Mars has to begin. Let us begin with the bad news. Picture yourself standing on the surface of Mars. Not in a film, not in a painting, but truly standing here, in a sealed suit, your boots pressing into a fine rust-coloured dust that has not felt rain in longer than complex life has existed on Earth. The first thing you would notice is the silence. The air is so thin, less than 1/100th as dense as the air you are breathing right now, that sound itself struggles to travel. A shout a few steps away would reach you faint and flattened, like a voice heard underwater. The second thing you would notice, if you could feel it, is the cold. The average temperature across Mars sits at around -60 degrees Celsius. On a pleasant summer afternoon near the equator, the ground at your feet might climb to something almost mild, while the air around your head stays bitterly frozen. And if you wandered toward the poles in the depth of winter, the temperature could fall past -120. This is a world where the seasons are measured not in warmth and chill, but in degrees of freezing. Now look up. The sky is not blue. In the daytime it glows a soft butterscotch, the colour of weak tea, because the same iron-rich dust that stains the ground also hangs suspended in the air. At sunset, strangely, the colours reverse. The dust scatters the light in a way that paints a cool blue glow around the sinking sun, so that a Martian evening ends not in red but in a pale, melancholy blue. It is beautiful. The atmosphere wrapped around this world is almost entirely carbon dioxide. There is barely a trace of oxygen, far too little to keep you alive for even a moment. Take off your helmet here, and you would not so much suffocate as simply stop, your lungs finding nothing to hold on to, and that thin blanket of gas does almost nothing to shield the ground. On Earth, we live beneath a deep ocean of air and a strong magnetic field, and together they soak up the constant sleet of radiation pouring out of the sun and in from deep space. Mars has neither. Its air is too thin, and its magnetic shield is long dead. That radiation is not a small thing, and it matters enormously for our question. On the surface of Mars, with so little air and no magnetic field to turn the charged particles aside, the ground is bathed in a level of radiation that would, over time, shred the delicate machinery of living cells. Any unprotected microbe sitting in the top layer of Martian soil would have its very molecules slowly broken apart by that invisible rain. This is one of the strongest reasons most scientists are confident that the open surface of Mars, the part the cameras can see, is not a place where anything is living today. It is not just cold and dry. It is actively, patiently sterilizing. And then there is the weather, in its own strange way. Mars is famous for its dust storms, and they are real, vast veils of fine dust that the winds whip up until every few years a single storm can swell to wrap around the entire planet and blot out the sun for weeks. In the films, these storms tear spacecraft apart, but the truth is gentler and odder. The air is so thin that even a furious Martian wind carries very little force. It would tug at you like a soft breeze that happens to be full of dust. The danger is not that the storm would knock you down. The danger is that it would smother the sunlight that a solar-powered machine needs to stay alive, and quietly let the cold creep in. So that is the verdict on the surface, delivered plainly. As a place to find something alive and thriving in the open, Mars today looks dead. Cold, dry, blasted, salted, and bathed in radiation. If you only ever looked at the surface, you would close the case, switch off the lights and go home, but the surface is only the skin of a world. And the story of Mars, like the story of so many quiet things, is far more interesting once you stop looking at the surface and start asking what it used to be, and what might still be hiding underneath. And the soil really is poison, in a very particular way, so let us add that to the list before we move on. Scattered through the Martian dirt are chemicals called perchlorates. They are a kind of salt, and on Mars they are everywhere, present at levels that would be toxic to most life as we know it. Perchlorates are aggressive. When they are warmed, they tear apart delicate carbon-based molecules, the very molecules that life is built from. Remember that fact gently and tuck it away somewhere safe, because in a little while it's going to come back and quietly overturn one of the most famous stories in the entire search for life on Mars. Now you might fairly ask why we are so fixated on Mars in particular. The sky is full of worlds. Why this one? And the answer is that Mars sits in a rare and precious category. It is the one other place in our entire solar system that we have good reason to believe was once genuinely Earth-like. Venus, our other neighbour, cooked itself into a furnace hot enough to melt lead. The moons of the giant planets are intriguing but deeply alien. Mars, though, Mars was once a world of liquid water and open sky, close enough to Earth in its youth that if you had stood on its shore 4 billion years ago, you might almost have felt at home. That is why we keep going back. Of all the worlds we can actually reach, Mars is the one that most looks like a place where the same thing that happened here might have happened there. Because Mars was not always like this. This is perhaps the most important thing to understand about the red planet, and it is one of the most beautiful. The dry, frozen, hostile world we just stood on is the ending of a story, not the whole of it. And the beginning of that story was almost gentle. Roll the clock back something like 3.5 to 4 billion years, and you would find a Mars you might not recognise. The evidence for this is carved right into the planet, where the rovers and orbiters can read it. There are dry river valleys, thousands of them. There are deltas, those fan-shaped spreads of sediment that form only where a flowing river slows and empties into a standing body of water. There are old lake beds and minerals that simply cannot form without liquid water having been present to make them. The early Mars was a world of rain, or at least of flowing and standing water. There were rivers, there were lakes. There may even have been a shallow ocean spread across the low northern half of the planet. Picture it for a moment, because it is worth the warmth on a cold night. A young Mars with a thicker sky, soft and perhaps faintly blue, rivers cutting down through the highlands and pooling in the craters, a great delta building grain by grain where a river poured into a quiet lake, laying down the very muds that a rover would come to read billions of years later. Clouds, maybe, shorelines, the slow, patient chemistry of a warm, wet world turning over and over in the sun. If life was ever going to find a foothold here, this was the moment, this long ago spring of the planet when Mars had everything to offer. Two places in particular have become the great reading rooms for this ancient chapter. One is Gale Crater, a vast bowl with a mountain rising from its centre, where one rover has been patiently working for well over a decade. The other is Jezero Crater, an ancient lake with a beautifully preserved river delta spilling into it, where a newer rover landed in the early part of this decade. Both craters were chosen for the same reason. Long ago they held water. Water sat in them, flowed through them, and laid down fine muds and clays at their floors. And clay, it turns out, is one of nature's gentlest keepers of secrets. On Earth, when something dies in still water and sinks into fine clay, the clay can cradle the chemistry of that life and hold it for an astonishing length of time. Clay protects, it seals, it slows the slow chemistry of decay almost to a stop. So when a rover finds clay-rich mudstone at the bottom of an ancient Martian lake, it is finding the closest thing this planet has to a library, with the books laid down billions of years ago and most of the pages still unread. But before we open those books, we have to face the saddest part of the story, which is how all of this ended. Because something went terribly wrong on Mars, and understanding what it was tells us almost everything about where life could still be hiding. The trouble in the end came down to size. Mars is a small world, only about half the width of Earth, and small worlds cool from the inside more quickly than large ones. Deep in its heart, the churning of molten metal that had wrapped the young planet in a protective magnetic field began to slow. And then, perhaps around 4 billion years ago, it faltered, and the magnetic shield of Mars died. Once that shield was gone, the planet lay bare to the sun. The solar wind, that ceaseless stream of charged particles streaming off our star, began to claw at the Martian atmosphere and strip it away into space. A little more each year, century upon century for hundreds of millions of years. The sky of Mars was slowly peeled off and scattered into the dark, and as the air thinned, the world could no longer hold its warmth, and it could no longer keep its water. The rivers stopped running, the lakes froze and then boiled away into the thinning sky, or sank down and froze solid underground. The shallow ocean retreated and vanished. Over an unimaginable stretch of time, a living-looking world dried out and chilled into the rusted desert we visited a moment ago. Mars did not die in an instant. It died slowly, over ages, the way a fire goes out when no one feeds it. And yet, here is the quiet hope buried in that ending. The water did not all simply disappear. A great deal of it is still there. Some is locked up as ice in the polar caps and just beneath the soil, and some, we are increasingly coming to suspect, sank downward and is still there, deep underground, where the planet's own warmth could keep it liquid. The surface dried. The deep did not necessarily follow. Keep that in your mind as we go, because it is the thread that everything else hangs from. Now we can open the books. For most of the history of Mars exploration, scientists could not even confirm that there was any homegrown carbon chemistry on the planet at all. Then, in the last decade or so, that changed. A rover in Gale Crater began to find organic molecules, the carbon-based building blocks that all known life is assembled from. Finding them does not prove life, because such molecules can also form through ordinary chemistry with no life involved at all. But it proves that the basic ingredients were there. Then, recently, came a genuinely striking result. Working with a sample of ancient mudstone drilled years earlier from a spot in Gale Crater that had once been a lake bed, scientists detected the largest organic molecules ever found on Mars. They have names that sound almost industrial: decane, undecane, and dodecane, and they are simply chains of carbon atoms, 10 and 11 and 12 atoms long, with hydrogen attached. What makes them quietly thrilling is what they might be fragments of. On Earth, chains like these often break off from larger molecules called fatty acids. And fatty acids are part of the membranes that wrap around every living cell. They are, in a real sense, part of the wall between a living thing and the rest of the universe. Now here honesty matters, so let's be careful. Those same chains can also be produced without any life at all, by hot water moving through rock. No one is claiming that this mudstone contains the remains of Martian creatures. What the scientists pointed out was something subtler and in a way more hopeful. They had been looking for amino acids, the building blocks of proteins, and they did not find them. They found these carbon chains instead, almost by accident. And the fact that molecules this large could survive, locked in Martian clay for around 3.5 billion years, tells us that if life ever did write its signature into these rocks, the rocks may have kept it legible all this time. The library is old, but the ink has not faded, so the picture sharpens. Long ago, Mars had liquid water sitting around for many millions of years. It had the organic building blocks, and as we will see, it had sources of energy that simple life could have fed upon. Water, building blocks, and energy. On Earth, wherever those three things gather together and linger, life appears with almost indecent speed, which leads to the obvious, aching question. If early Mars had everything life needs, and if life on Earth took hold the moment our own planet offered the same conditions, then did the same thing happen next door? And if it did any of it survive the long dying of the world, and is any of it still down there somewhere in the dark? To answer that honestly, we have to do something that does not come naturally to us. We have to talk about how badly we want it to be true, and how that wanting has fooled us before. Because the search for life on Mars is not a clean line of progress. It is a story of false dawns. 3 times now we have stood at a microphone, or at a press conference, or on the lawn of a great house, and very nearly told the world that we were not alone. And 3 times the universe has gently, patiently, shown us that we had jumped too soon. If we're going to weigh the evidence tonight, we have to walk through those near misses first. They are the reason scientists choose their words so carefully now. They're also, frankly, some of the best stories in all of science. The first and most haunting of them began in the summer of 1976, when 2 spacecraft named Viking 1 and Viking 2 became the first machines from Earth to land successfully on Mars and survive. They settled onto 2 different planes, a world apart from one another, and they carried something no Mars mission has truly carried since. They carried experiments designed not to study the rocks or the weather, but to directly ask the soil whether anything in it was alive. The cleverest of these was an experiment called labelled release. The idea behind it was simple and rather elegant. The thinking went like this: if there are microbes living in the Martian soil, they will be hungry, and like all living things they will eat and then give off waste gas. So the experiment scooped up a little Martian dirt and dribbled onto it a few drops of a nutrient broth, a kind of soup, with the carbon atoms in that soup made very slightly radioactive so they could be tracked. Then the instrument simply sat and listened. If something in the soil ate the soup and breathed out the carbon, that radioactive carbon would appear in the air of the little chamber and the detector would see it. And it saw it. On Mars, on both landers, a world apart, the soil was given its drop of broth, and the radioactive gas came rising out, exactly as if something hungry had just been fed. The signal was strong. It was quick. It looked to more than one scientist watching the data come back across the gulf of space, precisely like the breath of living things. For a few electric moments it seemed as though 2 small robots had reached out and touched life on another world. But science does not run on a single result, no matter how thrilling. There were other instruments on the Viking landers, and one of them was built to do something crucial. It was built to bake a sample of the soil and sniff the vapours, looking for the organic molecules, the carbon building blocks that any living thing would have to be made of. And that instrument found nothing, or at least nothing it could clearly identify, and that created an agonizing contradiction. One experiment seemed to be detecting the breath of life. Another seemed to be saying there was no life there to breathe because it could find none of the carbon chemistry that life requires. And those were not the only tests giving strange answers. The landers carried 2 further biology experiments alongside the labelled release. One offered the soil a richer broth and watched a sudden gush of oxygen come pouring off the dirt, faster and stranger than living things would explain, pointing towards some aggressive, lifeless chemistry in the soil itself. The other tried to see whether anything in the soil could quietly build itself out of the carbon in the Martian air, and got back only the faintest flicker. Neither a clear yes, nor a clean no. So the Viking landers came away holding a fistful of contradictions. One test that looked like breathing, one that looked like raw chemistry, one that simply shrugged. And no way, across all those millions of miles, to walk over and check the answer by hand. Faced with all of that, most scientists drew the cautious conclusion. They decided that the gas from the labelled release experiment was probably not the waste of living microbes at all, but the product of some strange, lifeless chemistry in the soil, a reaction that mimicked metabolism without any creature behind it. The Martian dirt, they reasoned, was simply chemically restless. It would have fizzed at the broth whether anything lived there or not, and so the most direct search for life ever attempted ended not with a yes and not with a clean no, but with a shrug, an ambiguous, unsatisfying, deeply frustrating shrug. Now here is where the perchlorate comes back, the poisoned salt I asked you to remember. Decades after Viking, a later lander scooped into the Martian soil and discovered that the dirt is rich in those perchlorates almost everywhere. And someone realized something uncomfortable. If you take soil full of perchlorate and you bake it, the way the Viking instrument baked its samples to look for organics, the perchlorate will violently destroy most of the organic molecules in the process, burning away the very thing the experiment was trying to detect. In other words, the instrument that found no organics on Mars might have been destroying the evidence in its own oven without anyone realizing it for 30 years. The carbon could have been there all along. We may simply have set fire to it before we could see it. That single realization reopened a door that most of the scientific community had quietly closed. And there was one man who had never accepted that it was closed in the first place. His name was Gilbert Levin, and he was the lead scientist behind the labelled release experiment. For the rest of his life, across decades, through papers and arguments and a great deal of professional loneliness, he insisted that Viking had found life in 1976. That the simplest explanation for a signal that looked exactly like metabolism was, in fact, metabolism. Most of his colleagues disagreed with him, and they may well have been right to. But he was never simply dismissed, because the data he was pointing at never went away. Gilbert Levin died in 2021, still convinced that 2 small robots had touched living things on Mars when he was a younger man, and that the world had talked itself out of believing it. And whatever the truth of the soil itself, something else happened in the aftermath of Viking that is worth pausing on. The ambiguity of that result frightened the people who planned these missions. The fear was that another inconclusive life detection experiment, another loud maybe, would damage the credibility of the whole endeavour. And so, for decades afterward, no mission was sent to Mars with a true, direct life detection experiment on board. The rover that found all those organics in Gale Crater was never designed to detect life itself, only to ask whether Mars could once have been a place where life was possible. We had reached out once in 1976, gotten an answer we could not interpret, and then, in a very human way, we stopped reaching out at all. We changed the question from "is there life there?" to "could there ever have been?" It is a quieter question. It is also, perhaps, a more comfortable one. The second false dawn came 20 years later, and this time the messenger was not a spacecraft but a rock. The story of it is almost unbelievable, so hold on. Long, long ago, an asteroid slammed into Mars and blasted chunks of the planet's crust off into space. One of those chunks drifted through the solar system for millions of years, fell at last through the skies of Earth, and came to rest on the ice of Antarctica, where it sat unnoticed until a team of meteorite hunters picked it up. They gave it a plain catalogue name, Allen Hills 84001, after the place and the year it was found. In the middle of the 1990s, scientists studying that little piece of Mars announced something astonishing. Deep inside the rock, under powerful microscopes, they had found tiny structures, long and segmented, that looked uncannily like fossilized bacteria. Tiny worm shapes, far smaller than any microbe known on Earth, but shaped so suggestively, alongside minerals and carbon compounds of the kind that life can leave behind. The claim was momentous. A rock from Mars, holding what might be the fossils of ancient Martian life. It made headlines around the entire world. The President of the United States stood up and spoke about it directly, telling the nation that if the discovery were confirmed, it would be one of the most stunning insights into our universe that science had ever uncovered. And then, slowly, carefully, the case came apart. Other scientists looked at those tiny worm-like shapes and pointed out that they were probably too small to be living cells at all, smaller than the smallest workable size for life as we understand it. They looked at the magnetic mineral grains that had been offered as evidence and showed that those crystals could grow in perfectly lifeless ways. And finally, more recently, researchers concluded that the carbon compounds inside the rock, the organic material that had seemed so promising, could be explained entirely without life. They had most likely formed when salty water seeped through the hot rock long ago and reacted with it, a slow chemical process with no living thing involved anywhere. The fossils of Mars dissolved on close inspection into beautiful, lifeless chemistry. Another maybe, another quiet retreat. So now you can feel the weight that sits on the shoulders of anyone who studies this question. Twice, the evidence looked like life. Twice, the simpler answer turned out to be chemistry. And this is the heart of how science actually works, which is something the dramatic version of the story always leaves out. Science is not really in the business of proving things true. It is in the business of trying, as hard as it possibly can, to prove things false. You take your most exciting idea, and instead of gathering reasons to believe it, you spend years hunting for every possible boring explanation that could account for what you see. And only if your idea is still standing after all of that, only if every dull alternative has fallen away, do you cautiously, grudgingly, begin to take it seriously. It is a discipline of doubt. It is slow, and it is humbling. And it is the single best tool our species has ever built for telling what is real from what we merely wish were real. Which brings us at last to the present and to the strangest, most carefully worded chapter of all. Because very recently, on the floor of that ancient lake called Jezero, a rover found a rock that has done something the others did not. It has survived the doubt. So far, the rover had spent years working its way across the crater floor, and then it drove into the dry channel of an old river that once fed the lake, into a region of pale, layered rock. And there, partly buried in that ancient riverbed, it found a single stone that scientists nicknamed Chayava Falls. To the camera, it was an arresting thing. Running through it were veins where water had clearly once flowed, and scattered across its face was a pattern of small spots. There were tiny dark specks the team called poppy seeds, and larger marks, pale in the centre with dark rims around them, that they called leopard spots. And those leopard spots made the scientists go very quiet and very careful, because on Earth, markings exactly like them are often made by life. Let me try to explain why, because it is genuinely beautiful chemistry. On Earth, there are microbes that make their living in a way utterly unlike the way you and I do. We breathe oxygen. These creatures, deep in mud and rock where there is no oxygen at all, breathe metal instead. They pull energy out of iron and other minerals, and as they do, they leave chemical fingerprints behind. In particular, they leave behind certain minerals that form when iron and phosphorus, or iron and sulfur, come together under their influence. And the rock from Chayava Falls held exactly those minerals, gathered into exactly those leopard-spotted rings, sitting right alongside organic carbon. It was the kind of pattern that, found in a stream bed here on our own world, a geologist would glance at and say, almost without thinking, that life made that. And there was a particular elegance to the way these spots are arranged that is worth lingering on. Each leopard spot has a pale heart and a dark rim, and that structure is a clue in itself. It looks like the frozen record of a tiny chemical reaction front, a place where one kind of chemistry gave way to another in a neat little ring, leaving the iron rearranged around the edge. On Earth, when hungry microbes sit in a patch of wet sediment and pull energy from the iron around them, they leave behind rings that look just like this, little halos marking where they fed. To see that same signature staring back from a Martian riverbed is the kind of thing that makes a careful scientist's heart beat a little faster, even as their training tells them to slow down. But the scientists studying this rock had learned the hard lessons of Viking and of that little meteorite. They knew that looking like life is not the same as being life, so they did the proper, patient, doubting thing. They sat down and tried with everything they had to prove that no life was needed to explain those spots. They asked, could intense heat have done this? The kind of heat from volcanic activity cooking the rock? They looked, and they found no sign that this rock had ever been that hot. They asked, could unusually acidic water have driven the chemistry instead? And here a tiny detail rescued them. Sitting near the sample was a grain of a green mineral that dissolves rapidly in acid. The fact that it was still there, intact, meant the water that touched this rock could not have been strongly acidic, because acid would have eaten that green grain away. One by one, the lifeless explanations were tested, and one by one they failed to fit. And so, in a peer-reviewed scientific paper, the team announced their result, and they chose every word like a surgeon. They did not say they had found life. They said they had found a potential biosignature, a pattern that could have been made by life. that they had genuinely tried and failed to explain any other way, but that still, on its own, on a planet whose chemistry we barely understand, could not be called proof. They had ruled out the obvious lifeless answers. They could not yet rule out some unfamiliar Martian chemistry that we simply have not thought of, because we have never had a living laboratory of a whole separate world to study before. It is worth understanding just how disciplined that caution is, because it tells you how the people closest to this question actually think. They have even built a kind of ladder for it, a scale that runs from the very first faint hint of something that might be life, all the way up at the top to multiple independent teams confirming more than once that life has truly been found. The Chayava Falls discovery sits low on that ladder. It is real. It is the strongest single case anyone has made from the surface of Mars, and it is still only a few rungs up from the bottom. The scientists are not being coy when they refuse to say the word life. They are being honest. They have been burned before, and they would rather be slow and right than fast and wrong. The rover did the one thing it could do. It drilled into Chayava Falls, pulled out a finger-length core of that precious spotted rock, sealed it inside a clean metal tube, and gave that sample a name of its own. The name is Sapphire Canyon. And then the rover set the tube down carefully and drove on, leaving it waiting on the floor of an ancient Martian river for the day when something might come to carry it home. Hold on to that image of the sealed tube waiting in the dust, because we are going to return to it, and when we do, it is going to break your heart a little. And the story did not stop there. As these very words are being prepared, only days ago, a fresh study landed in one of the great scientific journals, and it deepened the mystery still further. Using a different instrument on the same rover, a kind of laser eye that reads the molecular fingerprints of a rock without ever touching it, scientists mapped the carbon chemistry across those same spotted mudstones near Chayava Falls in far greater detail than ever before. They found organic carbon scattered all through the rock, hundreds of separate detections woven in among the minerals. It is the richest haul of organic matter ever read from the surface of Jezero, and, as far as anyone knows, the first time we've ever traced large complex carbon molecules directly across the natural face of a Martian stone. The same careful voices applied, of course. That instrument, reading the rock from a distance, cannot tell us whether the carbon was laid down by life or by lifeless chemistry. But here is the quietly staggering part. Rich organic carbon like this has now been found in two separate ancient lake beds on Mars, in Gale Crater and in Jezero, and those two craters lie more than 3,000 kilometers apart on opposite reaches of the planet, which means the ingredients for life were not some fluke of one lucky spot. They appear to have been laid down, generously, across the whole young face of the world. Wherever there was water, it seems, there was carbon. The raw material was everywhere. But notice something. Everything we have talked about so far, the organics, the leopard spots, the false alarms, all of it is about the ancient past. It is about whether Mars was alive billions of years ago, when it was warm and wet and young. That is a magnificent question. But it is not quite the question we started with tonight. We didn't ask whether anything was ever alive on Mars. We asked whether anything is alive on Mars right now, today, in the cold and the dark while you lie there listening, and that is a different question, with a different and far stranger answer. On the surface, as we have seen, the answer is almost certainly no. Nothing we understand could survive out in the open up there, under the radiation and the cold and the poison salts. But the surface, remember, is only the skin of the world. And it turns out that the deeper you go on Mars, the friendlier it gets. This is the great reversal at the centre of the modern search. To find a place on Mars where life could still be clinging on today, you do not look up or out, you look down. Start with water, because life as we know it cannot do without it. There is no stable liquid water on the surface of Mars now. The air is too thin and too cold, so any exposed water would freeze, or boil away, or both. There may be brief, thin films of extremely salty brine that form for a few hours in a few places, where salts pull a little moisture from the air. But these are so cold and so salty that, as far as we can tell, even the toughest life we know of could not make a living in them. So the surface is a dead end for water and for life alike. Go down though, and the story changes. The hints of buried water have been gathering for years, and each one is tantalizing in its own way. More than half a decade ago, a spacecraft sweeping the planet with radar reported a bright, strange reflection deep beneath the ice cap at the Martian South Pole. Exactly the kind of echo you would expect from a buried lake of salty water. The claim is still argued over because very cold, very salty water behaves in ways that are hard to pin down from orbit, and some scientists think the signal might come from ordinary rock instead. Then there are the dark streaks that appear on certain steep Martian slopes, darkening in the warm season and fading in the cold, which for years looked thrillingly like trickles of brine seeping down the hillsides. More careful study has cooled that excitement too, and many now suspect those streaks are simply dry sand and dust slipping downhill rather than flowing water. And most recently, the planet's own faint tremors have added their voice. A lander pressed a sensitive ear to the Martian ground and listened for years to the quiet shudders that run through the rock, the Mars quakes. And the way those waves travel, the way they slow and bend at depth, has hinted at something extraordinary. Several kilometers down, perhaps 5 to 8 kilometers beneath the surface, there may be a layer where liquid water still soaks the pores of the rock kept from freezing by the gentle warmth rising from the planet's deep interior. None of these clues is a certainty. All of them point gently and stubbornly in the same direction, down, toward water, toward the dark, and on Earth, wherever we find wet rock, even kilometers underground, even with no sunlight and no oxygen, we find life. This is one of the strangest and most wonderful discoveries of the last few decades, and most people have never heard it. Far beneath your feet right now, down in the deep rock of our own planet, there is an entire hidden world of living things, microbes that have never seen the sun, that breathe rock instead of air, that drink the thin films of water trickling between mineral grains, living slow, patient lives in the dark. Some of them may sit almost motionless for thousands of years between meals. Together they are thought to make up a huge fraction of all the living matter on Earth, a vast biosphere hidden where we almost never think to look. The deep is not dead. On our world, the deep is teeming. And here is the quiet, careful thought that follows, and I want to label it clearly as informed speculation rather than established fact, because no one has ever found such a thing on Mars. If life ever did arise on early Mars when the surface was kind, then as the surface slowly died, life would not necessarily have died with it. It could simply have retreated downward, following the warmth and the water into the deep rock, exactly the way it thrives in the deep rock of Earth. The surface would go silent and cold and bright with killing radiation. And life, if it was ever there, might still be down below, holding on in the warm, wet dark where we've never once drilled deep enough to look. And now, finally, the methane comes back. Remember the gas from the very beginning, rising and vanishing over the crater, seen by the rover and not seen by the orbiter. We still do not know what makes it. It could be made by ordinary geology, by water reacting with certain rocks deep underground, a process that needs no life at all. That is a perfectly real possibility, and it may well be the answer. But there is another possibility that we cannot rule out. On Earth, a great deal of methane is made by a particular kind of ancient microbe that lives without oxygen, deep underground, and breathes the gas out as its waste. They're called methanogens, and they are exactly the sort of life that could, in principle, survive in the wet rock far beneath the Martian surface. So when that faint breath of methane seeps up out of the Martian ground and then fades away, we are left with two possibilities standing side by side, and no way yet to tell them apart. It is either the planet breathing through dead chemistry, or it is something down there exhaling. And the methane only grows stranger the closer you look at it. The rover on the ground has watched the gas not only rise and fall with the seasons, but flicker on a daily rhythm too, creeping up in the cool of the Martian night and thinning away in the heat of the day, as though it seeps from the ground after dark and is scrubbed from the air by sunlight. That would help explain why the orbiter high above, taking its readings in full daylight, might miss what the rover catches at dawn. But there is a more unsettling possibility that some scientists have raised more recently, and honesty demands that we say it plainly. It is conceivable that the methane the rover detects is not really out there in the Martian air at all, but is leaking in tiny amounts from somewhere inside the rover's own instrument, fooling its exquisitely sensitive detector. If that were true, the great Martian methane mystery would dissolve into a problem of plumbing. No one yet knows, and with no new mission flying to settle the matter, the gas remains exactly what it has been for years, a breath we cannot explain. That might mean everything or nothing at all. That is the honest answer to the question we asked. Is anything alive on Mars right now? We do not know. Not on the surface, almost certainly. But beneath it, in the warm, wet, dark kilometers down, there is a real possibility that we cannot yet rule out, and a faint, maddening trace of gas in the air that might, just might, be a sign of it. The most truthful thing anyone can say is that we have not looked in the one place where the answer might actually be, and we have not yet built the kind of experiment that could tell life from chemistry once and for all. The question is not closed, it is simply unanswered, and there is a vast difference between the two. There is one more possibility hiding inside all of this, and it is the strangest of them all. So far we have spoken as though Mars and Earth were two separate stages, and the only question is whether life appeared on each of them on its own. But the two worlds have never truly been sealed off from one another. They have been trading pieces of themselves for billions of years. Every so often, a large asteroid slams into Mars hard enough to fling chunks of its crust clear off the planet and out into space. Some of those fragments wander the solar system for ages, and a few of them eventually fall to Earth. We have them in our museums right now. That little Antarctic meteorite from earlier in our story, the one that fooled us with its false fossils, was itself a piece of Mars that made exactly that journey. The traffic between the worlds is real, and it runs in both directions, and here is where it becomes dizzying. Microbes are tough, far tougher than you might imagine. Some of the hardiest ones we know can survive being frozen, dried out, starved and blasted with radiation for astonishing lengths of time, curled up and dormant, simply waiting. So imagine, on a young and living Mars, a rock full of sleeping microbes blown off the surface by an impact. Imagine it drifting cold and dark through space for a few million years, and then falling, burning, through the skies of an early Earth, and coming to rest in some warm, shallow sea. If anything inside survived that journey, then life on Earth might not have begun on Earth at all. It might have begun on Mars and ridden here on a stone. We tend to assume we're asking whether there is alien life next door, but there is a real, serious, scientifically discussed possibility that points the question straight back at us. That the first living things on our own world might have been immigrants. That the aliens, in the end, might be the ones telling this story and the ones listening to it. That we might, in the deepest possible sense, be the Martians, and Earth merely the place our most distant ancestors happened to land. No one knows whether it happened that way. It may well be that life arose here entirely on its own, in some warm pool or deep sea vent, with no help from anywhere. But the mere fact that we cannot rule the other story out tells you how deeply the fates of these two worlds are tangled together. They were born from the same cloud of dust around the same young sun. They were both warm and wet in their youth. They have been swapping rocks ever since. Whatever the truth turns out to be, Mars is not really a stranger we are studying from across the street. It is something closer to a sibling, an older brother who went out into the cold first and fell silent. And the question of whether it ever lived, or lives still, is quietly also a question about ourselves, about where we came from, and about whether the spark that lit us was ever truly ours alone. Step back for a moment and let yourself feel the full size of what is actually at stake here, because it is easy to lose it among the rovers and the rock names. For the whole of human history, we've had exactly one example of life in the universe. One, the life of Earth, in all its riot of forms, from the bacteria in a drop of pond water to the whale and the redwood, and you, lying there listening, is, as far as we have ever been able to prove, the only life there is anywhere. Every living thing we have ever met shares the same deep ancestry, the same basic chemistry, the same single family tree that runs back to one beginning. We have never once seen life start over, from scratch, anywhere else. Which is why Mars matters so much far beyond the red planet itself. If we were to find that life arose on Mars too, truly separately, a second independent spark struck on a second world right next door to ours, then in a single stroke the universe would change its character entirely. Because if life began twice in one ordinary solar system, around one ordinary star, then it becomes almost impossible to believe it did not begin 1,000 times, 1,000,000 times, everywhere the conditions were right, across the uncountable worlds of the galaxy. Life would no longer look like a freak accident that happened once. It would look like something the universe simply does, readily, whenever it gets the chance. A wet rock and a little time, and the cosmos begins to stir. There is an old, almost mathematical way of putting it. Life in the universe can really only come in one of three amounts. It can be 0, which we know is wrong, because here we plainly are. It can be 1, if Earth is a lonely miracle, a single candle lit once in all the dark. Or it can be many, perhaps beyond counting, if the spark is easy and the universe is full of it. We already know the answer is not 0. The whole weight of the question, then, comes down to telling the difference between one and many, and the most likely place in all the heavens for us to settle that question, the nearest world where a second beginning might have left its mark, is the cold red planet we've been visiting all night, and that is really why we keep going back, through failure and false alarm and heartbreak. It is not about Mars alone. It is about the oldest and loneliest question our species has ever asked, whispered upward on 100,000 nights since the first human looked at the stars and wondered, are we alone? Mars is the small, quiet, reachable test that might finally begin to answer it. A single rusty world, holding perhaps in the dark beneath its surface the most important secret there is. It is worth taking a moment here in the calm middle of the night to remember how astonishing it is that we can ask any of this at all. For almost all of human history, Mars was a wandering red point of light, a thing of myth and omen, a god of war scratched into the imagination of every civilization that ever looked up. We could not visit it. We could only wonder, and we wondered extravagantly. A little over a century ago, a wealthy astronomer peered at Mars through his telescope and became convinced he could see fine, straight lines crisscrossing its surface, and he decided they were canals, vast waterways dug by a dying Martian civilization to carry meltwater from the poles to their thirsty cities. He was wrong. The canals were a trick of the eye, a pattern the mind paints onto a blurry image. But the dream was so powerful that it launched 1,000 stories of Martians and invasions and red deserts full of ruins, and it shaped how we saw that planet for generations before a single spacecraft ever arrived. And then, within a single human lifetime, we stopped only dreaming and began to send pieces of ourselves across the void to touch it. The first were simple flyby probes, machines that streaked past Mars and snatched a handful of blurry photographs before sailing on into the dark, and even those first grainy images rewrote everything we thought we knew, sweeping away the canals and the cities and showing us a cratered, silent world. Then came the orbiters, settling into long looping paths round the planet, mapping it from pole to pole. Then the landers, the Viking pair among them, the first machines to settle onto the surface and survive. Then, at last, the rovers, the explorers that could actually move. A small brave one no bigger than a microwave oven that proved a wheeled robot could roam another world at all. Then a pair of larger rovers that were meant to last just 90 days and instead worked for years, one of them rolling across the rust for well over a decade before the dust finally took it. Then the car-sized rover still climbing its mountain in Gale Crater after all this time, and then the newest with the tiny helicopter folded beneath it. And these were not just cameras on wheels. They were tiny outposts of human cleverness, each one carrying some small piece of the future with it. One of them held a golden box, no bigger than a car battery, that breathed in the carbon dioxide of the Martian air and, through a patient bit of chemistry, breathed out pure oxygen, the first time we have ever made breathable air on the surface of another world. It made only a whisper of it, enough for a few minutes at a time, but the point was never the amount. The point was the proof that one day the air a Martian explorer breathes, and the fuel that lifts them home again, might be made from the planet itself rather than hauled all the way from Earth. And that little folded helicopter did something many people had genuinely doubted was even possible. It lifted off and hovered in an atmosphere so thin it should barely hold a blade, and then it did it again, dozens of times, scouting the ground ahead from the air. Every one of those firsts is a stepping stone, laid quietly down, toward the day the explorers are no longer machines. Behind every one of those machines stood thousands of people who will never set foot on Mars themselves, and who spent their whole careers making sure their robots could. To choose just one, the chief engineer of the program that runs the robotic exploration of the Mars, an engineer named Humphrey Price, known to nearly everyone as Hoppy, helped work out the brutal physics of landing those rovers safely on the surface, and has spent years designing the careful, frugal mission plans that might one day carry not robots but people to Mars and home again. The dreaming and the engineering are not separate things. They are the same impulse, pointed at the same red light in the sky. And that impulse spills naturally out of the laboratories and into our stories. It always has. Long before we had a single clear photograph of the place, we were writing tales of Mars, peopling it with canals and kings and invaders, asking through fiction the very questions the rovers now ask through chemistry. What is up there? Is it like us? What will we find when we finally arrive? That same chief engineer, the one who helped land the rovers, also lent a short science fiction story of his own to a printed anthology gathered around a single theme: what we might discover on Mars once we're living there. The collection is called Alien Dimensions, and its Mars colonization issue brought together imagined futures from many writers, including that real engineer who spent his days planning the genuine article. There is something lovely in that, in the same mind that calculates a descent trajectory, also sitting down to imagine the lives that might one day be lived under that butterscotch sky. The link to that anthology is waiting for you in the description below, if you would like to wander into those imagined Martian futures yourself once the night is over. That same engineer wrote something else recently too, in a sober chapter, for a 2026 book about our future as a spacefaring people. A chapter simply titled Transportation Architectures. And the heart of what he argues there is worth carrying with you, because it is not quite what you might expect from one of the people who actually builds these missions. For more than half a century, ever since we last walked on the moon, brilliant and workable plans to send humans to Mars have been drawn up again and again, and not one of them has ever flown. The obstacle, he points out, has rarely been the engineering. We broadly know how to do it. The true barrier, the one that has stopped us every single time, is money, and the will of governments to commit it, and to keep committing it, across the long patient years such a journey would take. That reference, too, is in the description for the curious, and hold the thought close, because it is about to come true in the most painful way imaginable. Because the future of real Mars exploration is at this very moment balanced on a knife edge. There are serious, detailed plans on the table to send human beings to Mars, perhaps as soon as the 2030s, plans worked out down to the launch windows and the fuel. There are new nations arriving at the Red Planet, and new private companies promising to build the ships. The story of Mars exploration is very far from over. In some ways, it is only now reaching its most dramatic chapter, the one where the explorers stop being robots and start being us. And yet, right now, in the present, something has happened that casts a long, strange shadow over all of it. And it brings us back at last to that sealed metal tube waiting in the dust. Remember Sapphire Canyon, the core of spotted rock from Chayava Falls, the single best piece of evidence for ancient life that anyone has ever gathered on Mars, sealed in its clean tube and set down gently on the floor of that ancient river to wait. The whole point of collecting it was that some questions simply cannot be answered by a robot on Mars, no matter how clever. To truly test whether those leopard spots were made by life, you need to bring the rock home into the great laboratories of Earth, where instruments far too large and delicate to ever fly to Mars could read its secrets atom by atom. There, scientists could look for the real fingerprints of life, the subtle ones a rover can never check. They could see whether the molecules lean overwhelmingly to one side, a handedness that living chemistry prefers and dead chemistry does not. They could weigh the kind of carbon and look for the particular balance that life on Earth always leaves behind. These are the tests that could finally tell breathing from chemistry, and every one of them needs the rock here in our hands. The plan to do exactly that, to send a mission to gather up the waiting tubes and carry them back across space, was for years the single highest priority in all of planetary science, and then, this year, it was cancelled. Caught in budgets and politics and the simple crushing expense of it, exactly the barrier that engineer warned of, the mission to bring those samples home was stripped of its funding and for now, abandoned. The hurdle was never the rocket. The hurdle was the will, and the will ran out. Which means that as you lie here listening, the answer to the question we have been circling all night, the rock that might finally tell us whether Mars was ever alive, is already in our possession. We've already found it. We've already drilled it, sealed it, and named it. It is sitting in a tube on the floor of an ancient Martian river, perhaps 140 million miles away, perfectly preserved, perfectly silent. And we have decided for now that we will not go and get it. The answer may already be in our hands. We have simply set it down in the dust and walked away from it. There is a chance, a real one, that another nation reaches its own Martian samples first, that the next pieces of Mars to be cradled in an earthly laboratory will have been gathered under a different flag entirely, while ours wait on, untouched in the cold. And there is a deeper echo here, one that runs all the way back to where we began. Because perhaps this is simply the thing we do. Perhaps in 1976, two small landers really did reach out and brush against living things in the Martian soil, and we spent the next 50 years explaining the feeling away. And perhaps now, having finally found the strongest evidence yet and sealed it in a tube, we will let it sit out there in the cold, unread, because the will to go and look turned out to be harder to summon than the cleverness to find it in the first place. It would be easy to find that bleak. I would ask you, in the quiet, to find it human instead. The search for life beyond Earth has never really been a search for microbes. It is a search for an answer to the loneliest question our species has ever asked. The question of whether, in all this enormous dark, anything else ever stirred. And the strange, tender truth that Mars keeps teaching us is that the hardest part of that search was never the looking. We are magnificent at looking. We have flung our eyes and our hands across the void and laid them on the soil of another world. The hardest part, it turns out, is being willing to believe what we find, to trust the faint breath of gas, to trust the spotted stone, to go back and check and risk the answer being yes. So tonight, while you drift off, let the red planet turn slowly in your mind. Picture the coal dust and the butterscotch sky, the dry rivers that ran billions of years ago, the warm, wet, dark kilometers down where something might still be holding on. Picture the small, sealed tube waiting patiently on an ancient riverbed for a journey home that may yet come, if we find the heart to send for it. We do not know if anything is alive on Mars right now, but we know the question is still open, and we know that somewhere out there in the silence, the planet is keeping its answer for us, holding it gently, the way clay holds a secret, until we are finally ready to listen. Sleep well. The rest of the universe will still be here in the morning, patient as ever, waiting for us to look again. Good night. There is a moon at the far edge of the solar system wrapped in thick orange air, and it has rivers. It has rain. It has clouds that gather and drift and break. It has seas that run out past the horizon under a heavy golden sky, and coastlines where a slow tide laps against a frozen shore. Everything about it sounds like somewhere you have been, and nothing about it is. And one day, if a quiet idea that has only recently been spoken out loud keeps on growing, a ship built by human hands may come falling out of the dark toward that orange world, slow itself against the pull of a great ringed planet, and settle onto a beach that no living eye has ever seen. Picture the beginning of that voyage. Not a tower of fire and thunder, not a chemical rocket screaming itself empty in a few violent minutes, but something stranger and far more patient. Imagine a spacecraft that carries a small caged star in its heart. Deep inside a chamber wrapped in magnetic fields, a faint violet light gathers and brightens and steadies and begins, very gently, to push. There is no roar. There is barely a sound. Just a thin blue thread of plasma streaming out behind, and a ship that will not stop accelerating for months until it has crossed more than 1 billion kilometers of nothing. That orange world is Titan, the largest moon of Saturn. And tonight, slowly and in order, we're going to take the entire journey. We will start with the engine that could finally reach it. We will cross the enormous gulf between here and there. We will fall past the rings of Saturn, and we will come to rest at last on the strangest shoreline anyone has ever imagined standing on. If you find it restful to drift off to the real science of faraway places, a quiet like and a subscribe will keep these journeys coming your way. Now settle in, let your shoulders drop, and let your breathing slow, because we are going a very long way from home. For almost the entire history of spaceflight, Titan has belonged to robots, and to dreams, and to very little in between. It circles the sun at around 1.5 billion kilometers, roughly 10 times farther out than the Earth, so distant that sunlight takes well over an hour to arrive. And when it does arrive, it is thin and pale, only about 1% as bright as the light you feel on an ordinary afternoon. A place that remote is easy to set aside as impossible for people. Beautiful, yes, worth a probe or two, certainly. But not somewhere you send a living crew. That old assumption has begun very recently to loosen. A 2026 gathering in Boulder, Colorado, the first meeting of its kind, brought planetary scientists and human spaceflight engineers together for 2 days around a single question. Not whether Titan is fascinating, since everyone in the room already agreed on that, but whether Titan could become the next place we travel to after the Moon and after Mars. And the people there were careful. Nobody stood up and promised footprints by any particular year. What they did instead was move Titan gently and deliberately out of the drawer marked fantasy and into the drawer marked someday, and then begin to write down, seriously and specifically, everything that someday would ask of us. How you would get there, how you would land, how you would build a shelter and power it and move around and step outside, what you would do once you arrived, how you would live on a moon where the weather is made of methane and the ground is made of ice. Their reasoning runs against a stubborn intuition, the feeling that farther away must always mean worse. Because one of the strongest arguments for Titan turns out to be the very thing that sounds most lethal about it: the thick, heavy orange air. We will come back to that, because it belongs with the rest of the case for why any sane person would cross the solar system to stand on a frozen moon. For now, hold on to the image of that ship and its caged star, because the hardest part of this whole idea is not the cold, and it is not the landing, it is the distance and the years the distance demands. The last spacecraft to make this crossing took about 7 years to reach Saturn, swinging past Venus, past Earth again, and past Jupiter, stealing a little speed from each planet as it went. 7 years is a perfectly reasonable timetable for a machine. It is an enormous thing to ask of a human crew. So the story of humans reaching Titan is, before it is a story about anything else, the story of an engine. A very particular engine, one that does not yet exist as finished flight hardware, but which already glows right now as an experiment in a laboratory. What is it, and how could it fold a 7-year crawl down into something a person could actually live through? Hold that question in the back of your mind. We will step inside that engine a little later once you have properly seen the world it is straining to reach. So, why Titan? Of all the places to aim a crewed ship, why choose one of the farthest? One of the coldest? The one most thoroughly drowned in haze? Let's begin with what Titan actually is, because it is genuinely one of the most alien and most familiar worlds ever discovered, both at once. It is the largest of Saturn's many moons, larger even than the planet Mercury, a giant among moons, and it is the only moon anywhere in the solar system that wears a thick atmosphere. That atmosphere is made mostly of nitrogen, the same gas that makes up the bulk of every breath you take. Earth's air is about 78% nitrogen. Titan's is around 95%, and the pressure down at the surface is only about 1.5 times the pressure at sea level on Earth. That last number is a small miracle for anyone thinking about visitors. On Venus, another world with a thick atmosphere, the pressure at the surface would crush you like a submarine imploding in the deep. On Titan, it would do nothing of the kind. The air is dense and calm and heavy, and it would press on you only a little more firmly than the water at the shallow end of a swimming pool. You would not need a rigid pressurized suit built like armor just to keep from bursting. You would mostly need to stay warm and to carry your own air to breathe. The temptation is to call Titan Earth-like, and in a narrow sense that is fair, but the resemblance is a disguise stitched together from the wrong materials. The temperature at the surface sits at around -179 degrees Celsius. At that cold, water is not a liquid and never could be. Water ice on Titan is not soft or slushy. It is frozen so hard that it behaves like rock, and the mountains, the pebbles, the bedrock of the whole moon are built from it. If you struck a stone of Titan ice against a block of granite, the ice would win. And yet Titan has liquid. It is the only other world we know of besides Earth, with stable pools of liquid standing openly on its surface. That liquid is not water. It is methane and ethane, the same compounds we handle as gases on Earth, chilled here until they run as cold, clear fluid. Titan has lakes of it. It has seas of it, hundreds of kilometers across. It has rivers that carve valleys and branch like the veins of a leaf, feeding down into basins that fill and shine. It has rain, real rain, that falls slowly through the thick air in fat drifting drops. It has a whole cycle of evaporation and cloud and rainfall and runoff that mirrors, almost exactly, the water cycle that shapes our own world, except that the working fluid would freeze a human being solid on contact. There is a lovely reason the methane behaves this way. Titan sits so close to the temperature and pressure where methane can be a solid, a liquid, and a gas all at once. That methane on Titan plays the same restless role that water plays on Earth, drizzling, pooling, evaporating, and drizzling again. It is a water cycle with the water swapped out for something that would kill you, running under an orange sky. Now here is the part that turns Titan from a curiosity into a candidate. Come back to that thick orange air. On most worlds, an astronaut's deadliest invisible enemy is radiation, the constant sleet of high-energy particles from the sun and from deep space that tears through living cells and through the delicate machinery of DNA. On the Moon, there is essentially no protection from it at all. On Mars, there is very little. But Titan is wrapped in an atmosphere about 50% denser than Earth's at the surface, and far, far deeper, stretching hundreds of kilometers up into the sky. That vast blanket of air is a natural radiation shield, the kind of shelter you simply do not get on the Moon or on Mars. It is so far from the sun and so deeply cloaked that the radiation which would be a constant menace elsewhere becomes, on Titan's surface, a much smaller worry. Stand on the ground there and the Moon's own sky is quietly looking after you. For the scientists thinking hardest about human beings living somewhere beyond Earth, that single fact may be Titan's greatest gift, and it is precisely the protection you cannot find anywhere else in reach. There is more. Titan's gravity is gentle, only about 14% of Earth's, less even than the pull of our own Moon. Combine that feather-like gravity with that thick, soupy air, and you get something almost whimsical. Titan is the easiest place in the entire solar system to fly, not in a rocket, in your own body. Strap a pair of wings to your arms, take a running start across the ice, and beat them down against that heavy air, and you could genuinely lift off and stay aloft. It is one of the very few places a human being could ever fly like a bird, and it is not a fantasy. It falls out of the plain physics of the air and the gravity, worked through by serious people. On Titan, a person could soar, and the ground beneath your feet would be a warehouse of raw material. Titan is drenched in methane and nitrogen and complex carbon chemistry. Those are the building blocks of fuel, of breathable gas, of the plastics and chemicals an outpost would need to sustain itself. A crew on Titan would be standing on top of a chemical supply that they could, in principle, learn to tap and turn into rocket propellant, so that the Moon itself might one day help fuel the journey deeper into Saturn's family of worlds and back home again. There is one disappointment waiting on that surface, and it is worth being honest about now, because you will feel its absence once we finally get down there. You would expect, standing on a moon of Saturn, to look up and see the great ringed planet hanging enormous in the sky, filling half of it, unbearably beautiful. You would not. The haze that makes Titan so hospitable to your body also seals off the view. From the surface, that thick orange air scatters and swallows the light so thoroughly that you would not see Saturn at all, and you would not even see the sun as a disk, only a general orange glow with no clear source. Saturn is up there, vast and ringed and silent, held in its fixed place in Titan's sky, and its reflected light does faintly tint the haze, a soft gift called Saturn shine, but the planet itself stays hidden behind the veil. To truly see Saturn from Titan, in all its glory, you would have to climb back up above the haze into orbit and look down through a break in the clouds. So that is the case. A world with a breathable pressure, a built-in radiation shield, resources scattered underfoot, and gravity light enough to fly in. The most Earth-like body we know of, dressed head to toe in materials that would kill you, waiting quietly at the far edge of the planets. The only real problem is getting a crew there alive and sane across a distance that beggars the imagination. Which brings us back, slowly, toward the engine. But before we open it up, there is somewhere you have to arrive first. To reach Titan, you must first reach the giant it circles. So let us go to Saturn. Before we ever go down to that orange surface, look up and out and let the ship carry you in toward one of the most beautiful objects in all of nature. Saturn is the 6th planet from the Sun, and it is enormous, about 9.5 times the width of Earth and around 95 times its mass. A pale gold world of hydrogen and helium so large that our entire planet could drop into it hundreds of times over. From a distance it glows a soft butterscotch, banded like Jupiter, but quieter, gentler, its stripes smeared into one another by a high golden haze. Its winds are savage, reaching well over 1,000 kilometers an hour near the equator, and yet from far away it looks utterly serene. A smooth ornament turning in the black. If Saturn were the only thing out here, it would still be worth the crossing, but of course Saturn is not famous for its size. It is famous for its rings. Nothing else in the solar system looks like the rings of Saturn. Up close they resolve into something almost impossible to believe. A vast flat sheet made of countless separate pieces, each one on its own orbit, each one circling the planet at its own speed. They're made almost entirely of water ice, bright and clean, and the pieces range from grains smaller than sand right up through snowballs and boulders to a few chunks the size of mountains, all of them orbiting together in a disk that stretches something like 280,000 kilometers out from the planet. And yet, for all that width, the main rings are astonishingly thin. In most places they are only about 10 meters from top to bottom. Think about that for a moment. A structure wider than the gap between the Earth and the Moon, and thin enough in proportion to put a sheet of paper to shame. If you could shrink Saturn down to the size of a dinner plate, its rings would be far, far thinner than that plate is thick. Fly close and you would find the rings alive with detail. There are broad gaps swept clean by small moons, delicate ripples and spiral waves raised by the tug of distant satellites, and strange faint spokes that appear and fade across the surface of the rings like the shadows of things that are not there. Tiny moonlets buried in the rings churn up wakes in the ice, like boats moving through a frozen sea, and the ice is slowly, endlessly raining down onto the planet below, a soft, continuous drizzle of ring material spiraling inward under Saturn's pull. As permanent and as ancient as they look, the rings may in truth be a passing thing, here for a chapter of the solar system's long life and destined, in some far tomorrow, to thin away to nothing. And then there is Saturn's strangest feature tucked away at its north pole. There, wrapped around the pole, is a storm shaped like a hexagon. Not a rough six-sided smudge, but a startlingly clean geometric figure, 6 straight sides and 6 sharp corners. The kind of shape you expect from a snowflake or a bathroom tile, not from the churning atmosphere of a giant planet. It spans about 30,000 kilometers, wider than the whole Earth, and it has turned there steady and geometric for as long as we've been able to look at it. Each of its 6 sides is longer than our entire planet is wide. At its heart spins a vortex, an eye many times larger than any hurricane on Earth, and over the long seasons of Saturn the whole hexagon slowly changes colour, drifting from a cool blue to a hazy gold as the light of a changing season works on the air. Nobody predicted it. Nothing else in the solar system does anything quite like it. It is exactly the sort of thing you would cross 1 billion kilometers hoping to see with your own eyes. Around this golden giant swarms a whole family of moons, well over 100 of them, more than any other planet in the solar system can claim. There is icy Enceladus, a small bright world that sprays great plumes of water out into space from cracks at its south pole, feeding one of Saturn's faint outer rings with a constant fountain of ice. There are dozens of smaller moons, shepherding the rings, carving the gaps, tumbling in the dark. And there, largest of them all, is the one we have come for, Titan, circling Saturn once every 16 days or so, held close on its long leash of gravity. For most of human history, nobody had any idea that the faint point of light beside Saturn was anything more than one more speck, and Titan itself may have been born in violence. A 2026 study built on careful computer simulations suggests that Titan is not a quiet leftover from the birth of Saturn at all, but the survivor of a catastrophe. In that picture, 2 older moons, one large and one smaller, once wandered onto crossing paths and slammed together in a single colossal collision, merging into the world we now call Titan. The impact would have been almost beyond imagining, an entire moon striking another and the 2 becoming one, resurfacing the new world so completely that it scrubbed away most of its old craters. And the same upheaval, in this scenario, may have flung out the debris that went on to build Saturn's bright rings, so that the rings you would cross on your way in and the moon you would land on could be children of the very same ancient disaster. It is still a hypothesis, a story told by simulations rather than settled fact, and it is one of the things a visit to Titan might one day put to rest. But picture it for a moment. 2 frozen worlds, closing on one another in the dark beside a ringed giant, and out of that single violent embrace this strange and beautiful moon. The story of noticing Titan is a short one, and it's worth telling quickly, because every step of it is a step toward the mission. It begins in 1655, when a Dutch astronomer named Christian Huygens, working with a telescope he had built himself, spotted a faint dot near Saturn and understood that it was a moon. For a long time that was all Titan was, a dot, a single entry in a lengthening list of moons, nothing to mark it out from the rest. Then in 1944 an astronomer turned a spectrograph toward that dot and caught something no one expected: methane. There was gas around Titan. It had an atmosphere, and moons were simply not supposed to have atmospheres, not real ones, not thick ones. That single detection changed everything, and it set off a slow, patient hunger to see what lay beneath the haze. Seeing beneath it proved maddeningly hard. The first spacecraft to fly through the Saturn system in 1979 confirmed that Titan was cold and that its atmosphere was substantial, but it was only passing through, and it could not part the veil. The next year, the spacecraft Voyager 1 arrived, and its path had been chosen with deliberate care to bring it in close to Titan. So close, in fact, that the encounter flung Voyager up and out of the flat plane of the planets forever, giving up any chance it might have had of going on to visit Uranus or Neptune. Mission planners judged Titan worth that price. Voyager confirmed the atmosphere was deep, dense, and mostly nitrogen, heavier than Earth's own air. And then it found, to everyone's frustration, that it could not see the ground at all. Titan hung in its cameras as a smooth, featureless orange ball, a locked door with no handle anywhere on it. The door stayed shut for years. In 1994, the Hubble Space Telescope, peering in wavelengths of infrared light that slip through the haze a little more easily, finally teased out the first hint of surface features, a bright continent-sized patch that was given the name Xanadu. Titan had geography after all. It was not a smooth ball, but the real answer had to wait for a spacecraft that would go there and stay. That spacecraft was Cassini, and it carried a small European probe named Huygens, after the man who first saw the moon. Cassini arrived at Saturn in 2004 and began years of long looping flybys, and its radar could finally pierce the orange veil, mapping the hidden ground strip by strip. And on the 14th of January in 2005, the Huygens probe detached, fell into Titan's atmosphere, opened its parachutes, and drifted down through the haze for 2.5 hours, sampling the air the whole way down. It became the first probe ever to land on a world in the outer solar system, and as it descended, its camera saw the ground, and the ground was extraordinary. There were pale rolling highlands, there were dark drainage channels, branching networks cut by flowing liquid, running down from the heights into flat dark plains. It looked, for all the world, like an aerial photograph of a riverbed on Earth on an overcast winter afternoon. When Huygens touched down, it did not crash. It settled with a soft crunch into a damp surface, scattered with rounded pebble of ice, smoothed and polished like river stones by liquid that had once tumbled them along. From orbit, Cassini went on to map the rest, and what it found rewrote the outer solar system. It found the lakes, dozens of them, and then it found the seas. The largest, called Kraken Mare, stretches something like 1,170 kilometers from end to end, larger than the Caspian Sea back home, a genuine sea of liquid methane and ethane, with a ragged coastline of bays and inlets and flooded river mouths. It found vast fields of dark dunes marching in parallel ridges around the moon's waist. It found clouds building and breaking, evidence of rainstorms, whole weather systems turning. It handed us at last a Titan we could begin to imagine standing on, a world of coastlines and seasons and rivers, running on methane where we run on water. Which is exactly what a certain group of scientists have now begun, quite seriously, to do. So how soon could any of this happen? This business of people rather than probes? Hold that question one more time. Because before a crew can cross to Titan, we have to solve the problem we set aside at the very beginning. We have to build the engine, and now, at last, it is time to open it up. Here is the difficulty, stated as plainly as I can put it. Chemical rockets, the kind that lift everything we launch today, are astonishingly powerful for a few minutes and then they are finished. They burn through their fuel almost at once in a great violent rush, and then they coast, silent and unpowered, for the rest of the trip, relying on the long, slow fall of gravity and the occasional slingshot past a planet to carry them the rest of the way. That is why the last mission to Saturn needed about 7 years, and a careful grand tour of the inner planets just to build up enough speed to arrive at all. For a robot, that is perfectly fine. For a crew, 7 years out and 7 years back is a brutal sentence, measured in radiation exposure, in tons of supplies, in the sheer psychological weight of all that dark. To carry people, you need an engine that does almost the opposite of a chemical rocket. Not one brief, violent shove, but a gentle push that never stops, a thrust so patient and so enduring that it goes on accelerating the ship for months on end. And the most tantalizing candidate for that job is an idea that sounds like something out of the far future, yet is already glowing quietly in a laboratory today. It is called a direct fusion drive. Fusion is the process that powers the sun and every star in the sky. It is the forcing together of the lightest atomic nuclei until they merge, and in that merging they release a tremendous flood of energy. For most of a century we have chased fusion as a source of clean electricity here on the ground, and it has been famously, maddeningly difficult. But there is another way to use it, one that turns out to be beautifully suited to space. Instead of using a fusion reactor to make electricity to sell to a city, you let the hot, fast particles stream straight out of the back of the reactor as exhaust. The same single machine then gives you two things at once: a steady push to drive the ship forward, and a river of electrical power to run everything aboard. Thrust and power from one caged star. The particular design being studied grows out of an experiment at the Princeton Plasma Physics Laboratory. Its heart is a device that holds a small cloud of fusion fuel, a blend of a heavy form of hydrogen and a rare, light form of helium trapped inside a bottle made of magnetic fields. Radio waves pour energy into that cloud until it becomes a plasma hot enough for the nuclei within it to begin to fuse. The magnetic field is shaped so that it opens at one end into a kind of magnetic nozzle, and the hot plasma streams out through it, pushing the ship gently forward. There is no great gout of flame. Picture instead a chamber ringed with heavy coils, a fierce, contained glow held in the grip of invisible fields, and a thin, bright jet of plasma trailing away into the black. Quiet, efficient, and unlike almost anything before it, able to run for month after month. There is a further elegance to the particular fuel it would burn. It is chosen to release most of its energy as charged particles, rather than as a storm of neutrons, which means far less of the harmful radiation that plagues other kinds of fusion, and a cleaner, safer engine to sit behind for years. Now here is what a drive like that could do for a trip to Titan. Engineers have taken this concept and worked out, in careful detail, what it could do on a real journey to Saturn's largest moon. The numbers are startling. A ship built around this kind of drive could reach Titan in a little under 2 years running its engine continuously, or in around 2.5 years using a gentler profile that thrusts for a while, then coasts, then thrusts again to slow down at the far end. Set that against the 7 years the last mission needed, and you can feel the whole idea shift beneath you. Something that took the better part of a decade becomes a voyage of roughly 2 years, and it could carry not a tiny probe but a substantial payload, well over a ton of spacecraft and cargo, along with all that electrical power waiting at the other end to run instruments and lights and life. And the real magic is in the slowing down. A chemical ship arriving at Saturn has a terrible problem. It is moving far too fast, and it has almost nothing left to brake with, so it can only scream past or fling itself into a wide, awkward capture. A fusion drive can do something a chemical rocket simply cannot. It can turn itself around and thrust against its own motion for weeks, shedding speed as gracefully as it gained it, easing the ship into orbit rather than hurtling by. That ability to decelerate, to arrive under full control, is the quiet breakthrough that turns a fleeting flyby into a place you can stay. I want to be careful and honest with you here, because good science demands it. This engine is not sitting on a launch pad today. What exists right now is the experiment, that magnetic bottle at Princeton which has heated its plasma to real and encouraging temperatures in short pulses, along with a set of detailed studies worked out on paper. The finished flight engine, the one that would actually carry a crew across the solar system, has not yet been built, and there is hard work between here and there. And when those scientists gathered in Boulder to talk seriously about people on Titan, the propulsion they leaned on most heavily for the nearer term was not fusion at all. It was a scaled-up nuclear electric system, a more conservative design descended from reactors being developed for missions closer to home, one that might make the crossing in around 500 days. The fusion drive is the bolder dream standing just behind that more cautious plan, the engine that, if it can be made real, would open not only Titan but the entire outer solar system to human beings and beyond. But dream or not, it gives us the shape of the voyage, so let us stop describing the engine and start using it. Let us light it and go. The departure itself would be unlike any launch you've ever watched. There would be a chemical rocket at the very start, of course, the brute force needed to shove free of the Earth and climb up out of the deepest part of our gravity. But once the ship is clear, out in the smooth dark beyond the moon, the real engine takes over and everything changes. The violence ends. The star in the ship's heart lights. That faint violet glow steadies inside its magnetic chamber, and the thin blue thread of plasma begins to stream away behind. And then the ship simply, gently, endlessly accelerates. There is no sensation of speed out there, no rush of scenery, nothing to mark the miles going by. Just a soft, constant, barely there push, a small fraction of the gravity you're used to, pressing you toward the back of the ship, hour after hour, day after day, week after week. That faint push is the whole secret. Because it never stops, it builds and builds, and the ship climbs to speeds no chemical rocket could ever reach. And it does it so patiently that human body never feels strained. You would float through the cabins in something close to weightlessness, with just the ghost of a downward tug to tell you which way is back. The crossing itself is the great test of the whole idea, and it is a test of endurance far more than of raw engineering. For most of 2 years, home shrinks behind you. The sun, which fills the sky over the earth and warms your face, dwindles until it is only the brightest star among many, a fierce white point that no longer warms anything at all. The radiation of deep space is always out there in the long dark between the planets, and so the ship is built to answer it. Often the plan is to wrap the crew's living quarters in the mission's own stores of water, because water is an excellent shield against radiation, so that the crew sleeps and eats and passes the long months cocooned inside the very water they will later drink. The fusion drive's steady river of electrical power runs the lights, the air, the warmth, all of it drawn from that same caged star, so that the ship is not coasting dead and cold through the void, but living, humming, powered and warm the entire way. That, more than anything, is what a fusion engine buys a crew. Not just speed, but a ship that stays alive around them. And then, slowly ahead, a new light begins to grow. At first, Saturn is just another star, one point among thousands, indistinguishable from the rest. Then it is a point with something faintly odd about it, a tiny bright bead that will not quite resolve. Then, through the ship's windows, it hardens into a disk, and the disk grows a fine line across it, and the line opens into rings, and week by week the most beautiful object in the solar system swells until it fills the view. A vast banded golden world cradled in a halo of ice, so bright and so strange that the crew would gather at the port simply to look at it, the way sailors once gathered at a rail to watch a coastline rise. Now the engine earns its keep a second time. The ship turns and thrusts against its own tremendous speed, and for weeks it breaks, bleeding away velocity until Saturn's gravity can take a gentle hold of it and swing it into orbit. And for a while the crew would simply be there, held in orbit around Saturn, closer than any human being has ever been, seeing with their own eyes everything the old robotic missions saw and more. The rings would stretch across the sky, no longer a picture on a screen, but a place, close enough to pick out the gaps and the ripples and the slow tumbling of individual chunks of ice, each one a tiny moon. The banded face of the planet would turn slowly below, its golden storms drifting. Somewhere down there, the great hexagon would be spinning at the pole, and out ahead, on its own orbit, would hang the real destination, a soft orange sphere, featureless and smooth and secretive, exactly as it looked to Voyager all those years ago. Titan, seen at last with human eyes, and still, even now, hiding its surface behind its veil. There's only one way to find out what is under that veil. You have to go down through it. The descent to Titan is, in one strange way, easier than landing almost anywhere else, and in every other way it is a plunge into the deep unknown. It is easier because of that thick, generous atmosphere. On a world with thin air like Mars, landing is a nightmare, because there is barely enough atmosphere to slow you down, and yet just enough to burn you up, and every spacecraft has to thread a terrifying needle to survive the fall. Titan is kinder, its atmosphere is deep and dense and forgiving, so a descending craft has plenty of air to push against. A ship can slow itself high up, open parachutes, and drift the rest of the way down almost lazily, sinking through the haze rather than slamming through it. The very thickness that hides the surface is the same thickness that lets you land softly upon it. So you fall, and as you fall, the orange closes over you. For the first long stretch there is only haze, a directionless amber glow with no sharp shadows and no visible sun anywhere in it, thickening as you sink through layer after layer. This haze is a smog of complex carbon molecules, built high in the atmosphere where sunlight breaks methane apart and the fragments recombine again and again into ever larger particles that then drift slowly downward, a permanent, gentle snow of organic material that has been settling onto Titan for longer than there has been life on Earth. Over the ages, it has buried the whole moon under its own slow exhalation. There is a genuinely eerie thing about the light down here, one of those details that quietly tells you how alien this place truly is. On Titan, the twilight can be brighter than the day, because the atmosphere is so deep and the haze scatters light so strongly around the curved edge of the moon. The sky near the horizon at dusk can actually outshine the sky straight overhead at noon. It is a trick of light found nowhere else in the solar system, and it means that the whole rhythm of brightness you have known your entire life is, on Titan, quietly turned inside out. Then, in the last few kilometers, the haze thins just enough and the ground rises up to meet you, and it looks, almost heartbreakingly, like home. Pale, rolling highlands, dark branching channels cut by rivers, a flat plain stretching away toward a hazy horizon. Your brain, trained by a whole lifetime on Earth, reaches out to name it all: riverbed, coastline, shore, valley, and every single name is almost right and completely wrong. You land, and now stand on Titan for a while and let yourself feel it, because the sensations would be like nothing in all of human experience. The first thing is the cold, though you would never feel it directly through a proper suit, and you had better hope you never do. It is around minus 179 degrees Celsius out there. That is far colder than the coldest night ever recorded anywhere on Earth. Colder by a wide margin than the deepest Antarctic winter. It is a cold that would freeze the water in your body almost at once, that would turn living tissue as hard and brittle as the ice underfoot. Titan would not chill you the way a hard winter chills you. It would freeze you the way liquid nitrogen freezes a flower, completely, instantly, and forever. The next thing you would notice is the strange lightness. The gravity here is only about 1/7 of Earth's, so you would weigh almost nothing at all. A person who weighs 80 kilograms at home would feel, on Titan, like a child of 11 kilograms. Every step would carry you up and forward much farther than you intended. A casual push of your legs would launch you into a long, slow, floating bound, and coming back down would take a strange, dreamy extra moment, and that thick air, pressing at 1.5 times Earth's pressure, would wrap around you like a warm, heavy fluid, except that it is not warm at all. Between the feather gravity and the soupy air, you truly could fly. Fix a pair of broad wings to your arms, run a few loping, bounding steps, beat down hard against that dense atmosphere, and you would lift clean off the surface of another world under your own muscle power. Of all the impossible sounding things about Titan, that one is real, and it may be the single most wonderful fact in the whole story. On Titan, a human being could take to the air like a bird. The ground beneath your boots would be water ice, but not ice as you have ever known it. At this cold, it is hard as stone, and it forms the bedrock, the hills, the scattered pebbles, and the mountains, some of which rise 1 kilometre or more above the plains. In the wide equatorial regions, you would find yourself among the great dunes, long parallel ridges of dark organic sand reaching perhaps 100 meters high, marching in ranks toward the horizon, sculpted not from pale silicate grains like a desert on Earth, but from dark, soot-like particles that drifted down out of the sky over the ages. These dunes may be shaped by rare, powerful winds that only rise every so often as the long Titan seasons turn, so that for years at a stretch they lie perfectly still, waiting. Walk among them in the low gravity, and the fine dust your footsteps kicked up would hang in the thick air far longer than dust ever hangs on Earth, and then settle back down with a slow, unhurried grace, like dark snow drifting through syrup. And if your path took you to the edge of one of Titan's seas, to a shore of Kraken Mare, you would stand at the margin of a body of liquid methane larger than the Caspian, a dark and almost perfectly still expanse stretching out under the orange sky until it faded into the haze. On Earth, wind whips any open water into waves within minutes. On Titan, the seas lie mostly glass smooth. their surfaces so calm that from orbit the radar saw them as polished mirrors, dark, flawless sheets set into the ice. Every now and then, as the long seasons turn and the winds slowly strengthen, the faintest ripple may cross them, the barest hint that they might one day stir, but mostly they simply lie there, dark and patient and unimaginably cold. If you waded in and your suit somehow let you, you would not float the way you float in water, because liquid methane is far lighter than water, and it would offer your body almost no support at all. And the moment your warm suit touched that cryogenic sea, the methane around it would boil furiously into gas, wrapping you in a churning cloud of vapour, a small, violent argument between the warmth of a living thing and a liquid nearly 200 degrees below freezing. Toss a pebble into that sea if you could, and even the sound would reach you changed, slow and deep and strange, because sound itself travels differently through that heavy cold air, lower in pitch and carrying farther, as though the whole world were speaking to you in a quieter, deeper register, close against your ear. And over all of it hangs the silence. There are no birds here, no insects, no rustle of leaves, no lapping voices of a living world. Apart from a rare, thin sigh of wind, there would be nothing to hear at all except your own breathing and the soft workings of your suit. A stillness older and deeper and more complete than anything that has ever existed on Earth. And there is one more thing about Titan that would draw a human crew across all that emptiness, and it lies out of sight, far beneath the ice. For many years, scientists believed that under Titan's frozen shell lay a vast global ocean of liquid water, a hidden sea wrapped clear around the moon's rocky core. That idea came from measurements made by the Cassini spacecraft back in 2008, and it made Titan doubly astonishing. A world with seas of methane on the outside and an ocean of water sealed within. But science keeps its picture honest by revising it, and a 2025 reanalysis of that old Cassini data told a subtler tale. It found that the way Titan flexes under Saturn's tremendous tides did not fit cleanly with a single deep global ocean. Instead, Titan's interior may be better described as a thick, cold slush of ice, laced with scattered pockets of liquid water, some of them surprisingly warm, perhaps warmer than a mild spring day, sitting near the heat of the rocky core far below. That might sound like a lesser thing than a grand hidden sea, but for anyone hunting for the possibility of a life, it may be better rather than worse. In small warm pockets, the ingredients that life would need are concentrated together rather than diluted across an entire ocean, gathered close instead of scattered thin. Whether anything has ever stirred in those dark, warm, buried pools, no one knows, and no telescope and no orbiter is ever likely to tell us for certain. It is one of the great open questions of the outer solar system, and it is exactly the kind of question that, in the end, only people standing on the ground, drilling, sampling, deciding in the moment what to chase, may finally be able to answer. As the scientists themselves put it, our robots can carry us only so far. In the end, a curious human being remains the finest instrument of exploration we have ever built, and Titan keeps offering up fresh mysteries faster than we can solve the old ones. Not long ago, astronomers turned the great new space telescope, the James Webb, toward Titan, and found a narrow window in the infrared where the haze thins just enough to glimpse the actual ground below. In that window they caught something strange, a distinct fingerprint pressed into the light reflected from the surface, the unmistakable mark of some material soaking up one precise colour of infrared. And when they went looking for what could leave that mark, comparing it against every relevant ice and compound ever measured in a laboratory on Earth, they found no match at all. Whatever is painting that signature onto Titan's surface, we have simply never seen it before. There is something down there, spread across the frozen ground that we cannot yet name. It may be some exotic frost, some product of that endless organic snowfall, arranged by the deep cold into a shape no laboratory has ever managed to make. Solving a riddle like that may take a machine that can land on Titan, scoop up the frozen ground, and taste it directly. And that machine is already being built. People, of course, will not be first. Before any crew ever crosses to Titan, that machine goes on ahead. 2028's Dragonfly mission is a nuclear-powered flying machine about the size of a small car, a craft with 8 rotors that will do something never attempted before on another world. It will fly. Set to launch on a heavy rocket for a cruise of about 6 years, it is on course to reach Titan in 2034. Drop through that thick orange air, and then leap from place to place across the surface, hopping in a series of flights from the dune fields of a region called Shangri-La toward a great impact crater named Selk, a scar some 90 kilometers across where, long ago, the heat of the impact melted the ice and let liquid water and Titan's rich organic chemistry mix together for a time. Over a mission of a few years, it would visit dozens of sites and travel well over 100 kilometers, sampling the sand with its instruments, sniffing the chemistry of the ground, listening with a seismometer for tremors deep in the ice, and photographing a landscape no camera has stood in since Huygens fell silent. It is the real, funded, dated first step, the machine that goes ahead to light the way. Everything else, the crew, the fusion engine, the outpost under the orange sky, still lies out beyond it, in the country of things not yet built. And so we come back at the end to where we began, to that ship falling out of the dark toward a moon wrapped in orange air. It is worth sitting for a moment with how strange and how deeply human this whole idea really is. Titan is about as far away as the imagination can comfortably stretch, a frozen world of methane rain and hidden warm pools and a sky that never once shows you the sun. By every ordinary measure it should be beyond our reach, filed away forever under the heading of impossible. And yet here we are in a quiet conference room in Colorado, and in a softly glowing experiment in a laboratory, and in the careful pages of mission studies, beginning to speak of it not as a dream but as a destination. Not because reaching it is easy, but because it is there, and because stretching toward the thing just past the edge of the possible is one of the oldest and steadiest things our species has ever done. Maybe it takes the engine we spent so long with tonight, the caged star, the patient fusion fire that could fold years down into months. Maybe it takes something else entirely, some idea not yet dreamed, waiting further along the road than any of us can see. When will all of it truly happen? The crossing, the descent, the first human footprint pressed into that ancient ice. Honestly, no one knows. Perhaps not soon, perhaps not in our lifetimes. But the direction has been set and the first scout is already taking shape in a clean room on Earth, and Titan will wait, as patient as it has been for 4.5 billion years. Its seas will lie still and dark under the haze. Its rivers will run their slow, cold courses, and the methane rain will go on drifting down through the orange twilight onto a shore that is, for now, still waiting for its very first visitor. If you enjoyed drifting all the way out to Saturn tonight, a gentle like and subscribe will carry the next journey to you when you are ready for it. For now, let the last image settle softly in your mind. A great ring giant turning in the dark, a quiet orange moon beside it, veiled and still. And somewhere in the years ahead, a small ship with a star in its heart, crossing the long night between them, carrying us at last toward the strangest and most beautiful shore we have ever dared to reach. Before we leave Titan, there is one more journey to make, and this one does not need a rocket. We have looked at Titan as scientists see it now, a distant world of ice and organic chemistry, of methane seas and deep engineering problems. We've imagined the long voyage it might one day take to send people there. But Titan has been a human destination for far longer than any of that, not in fact, but in story. Long before anyone gathered in a conference room to work out how a crewed mission might really function, writers and filmmakers had already been landing us on that orange moon in their imaginations, building spaceports and colonies and lonely research bases beneath its haze. So as our scientific journey settles toward its close, let us look back at the ways we have dreamed our way to Titan, and notice something rather lovely along the way, that those dreams slowly grew up alongside the science. In the earliest days of television, Titan was barely a world at all. It was a name on the frontier. In a 1953 episode of the American series Space Patrol titled Fraud on Titan, the moon is not a place of strange chemistry, but a busy outpost of human commerce, a settlement with a spaceport and fuel depots, important enough to the trade of the outer planets that it is worth scheming over. One of the show's own introductions described Titan simply as Saturn's sixth moon. Grown important to the commerce of the outer worlds, there is no methane rain here, no organic dunes. Titan is remote enough to feel exotic, yet familiar enough to hold a fuel station and a swindle. That is how the frontier always begins in our stories, as somewhere just far enough away to be dangerous and just close enough to be ours. By the 1970s, the dream had grown colder and lonelier. In a 1977 Doctor Who adventure called The Invisible Enemy, Titan has become an isolated base perched on the edge of human reach, a refueling station crewed by a handful of people with no help anywhere close. A distress call crackles out of the dark. Mayday, Mayday, this is Titan Base, and something has gone terribly wrong. It is a shape of story we return to again and again, the far outpost where the systems fail and no rescue can arrive in time, because the distance itself has become the monster. A 1985 film released as Creature, and also as The Titan Find, took the same idea further still, sending an expedition to Titan only to have it wake something buried and predatory in the cold. Titan, in these years, was where humanity went to be small and alone and afraid. Then, in 1997, Titan became something quite different. It became a wish. In the film Gattaca, we never once see the moon. We never even leave Earth. And yet Titan hangs over the entire story, because reaching it is the single thing the main character wants more than anything else, a place on a mission to Saturn's largest moon. For a man told from birth that his genes had already decided the size of his life, that voyage to Titan becomes proof that a person is more than the prediction written into them. Here Titan is not a spaceport or a haunted base. It is the far edge of human aspiration, the distant light a person reaches toward in order to prove that the reaching itself is real. And as the science of the true Titan came pouring in, from Voyager, from Cassini, and from the little Huygens probe that actually touched the surface, the stories began to lean on that knowledge. In the television series Eureka, a mission named Astraeus prepares the first crewed flight to Titan, and suddenly the storytelling fills with the texture of real spaceflight. The crew selection and the endless interviews, the strain on the people left behind, the sleeping pods meant to carry a crew through the long dark. In the 2018 film The Titan, set on a crowded and failing Earth, the moon becomes humanity's chosen refuge, and the whole drama turns on the terrible cost of adapting a human body to survive its cold and its thick, strange air. And in its closing moments, that transformed human does the one thing this moon has always quietly promised. He spreads his arms over a methane lake, and he flies. Most recently, in the 2024 film Slingshot, the journey itself becomes the whole story, a voyage of years toward Titan aboard a small ship, where the real danger is not the cold outside, but the slow unravelling of a mind kept too long in the dark between the planets. It is, in a way, the most honest fiction of them all, because it worries about exactly the thing the engineers now worry about, not whether we can reach Titan, but whether the people we send will arrive still themselves. Look at the whole sweep of it and you can watch an idea growing up. Across more than 70 years, Titan has been imagined as a trading post, a doomed base, a lair of something monstrous, a private dream of freedom, an organised expedition, a last refuge, and a test of the human mind. Each generation reached for the moon with the tools it had, and each new discovery about the real Titan handed the next set of dreamers a truer world to dream about. And now comes the strangest turn of all. No crewed mission to Titan has been approved, no astronauts have been chosen, and no ship waits on any launch pad. What exists is an idea, carefully argued and quietly gathering weight, that one day, perhaps long after we have found our footing closer to home, people may truly begin the long fall towards Saturn. The storytellers have simply been there first, sending imagined travellers ahead of the real ones for the better part of a century. And when the first true crew finally crosses that great dark gulf and looks up at Saturn from the orange edge of Titan, they will be arriving somewhere the human mind has already visited, over and over in the quiet of 1,000 stories. For tonight, though, we can let the moon be both things at once, the world the telescopes are still puzzling over, and the one our dreams keep gently landing on. Rest now, somewhere in between the two, and we will meet again, out among the far worlds very soon.